7 miles across, carved from ice older than Earth itself, a silent Voyager is drifting through the vast emptiness of space, a speed that would make even the fastest human-made probe seem sluggish. It traces a path so precise it almost feels deliberate, skimming past Mars, looping behind the Sun, brushing near Earth, and slicing through Jupiter's magnetic field. This is Threeey Atlas. But what if it's not just a random fragment of cosmic debris? What if this icy interloper carries the fingerprints of a civilization far older and far stranger than anything humanity has ever known? Could Threeey Atlas be a relic, a message, or even a tool sent across the stars, waiting for its moment to reveal the existence of intelligent life beyond our own? Before we start, leave a comment and let us know where you're watching from and what time it is there. Now, settle in for a journey to the most mysterious asteroid we have ever discovered. Imagine a visitor from far beyond our solar system, passing silently through the cosmic neighbourhood we call home. This visitor is known as Threeey Atlas, and it is unlike anything we see every day. It is only the third confirmed interstellar object ever detected travelling through our solar system, a rare cosmic traveller from a distant star system. Its very name carries meaning in the world of astronomy, hinting at both its origin and its fleeting presence. Unlike the comets and asteroids that are permanent members of our Sun's gravitational family, Threeey Atlas is merely passing through. Its path is hyperbolic, a one-time journey that guarantees it will never return. Because it is only briefly visiting, scientists have a limited but extraordinary chance to study material formed around another star. This object has not been altered by the processes that shaped our solar system, offering a glimpse of something truly alien. The name itself is a story in 3 parts. The 3 shows that this is the third interstellar object ever recognised, following 1e Oumuamua, discovered in 2017, and 2a Borisov, spotted in 2019. The I stands for interstellar, a classification reserved for objects with clear evidence that they come from beyond the Sun's domain. Finally, Atlas honours the survey that first spotted it, the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a sky-scanning program primarily designed to detect Earth-threatening asteroids. While its main mission is planetary defence, Atlas has unintentionally become a pioneer in finding alien visitors. The discovery of Threeey Atlas was an electrifying moment for astronomers. On December 12, 2019, the Atlas telescope system in Hawaii detected a faint, fast-moving point of light drifting against the backdrop of stars. At first, it was catalogued as an ordinary comet, appearing just as a faint, hazy blur, but further observations revealed a startling truth. Its orbit was not the usual elliptical path that ties comets to the Sun. Instead, it followed a hyperbolic trajectory, meaning it was visiting only once and was unbound by the Sun's gravity. By running the orbital calculations backward, scientists confirmed that this was no ordinary comet. Like Oumuamua and Borisov before it, it had arrived from interstellar space. Detecting interstellar objects is notoriously difficult. They are small, dark, and move incredibly fast, so most pass through unnoticed. The fact that Atlas spotted Threeey at all is a testament to the incredible sensitivity of modern sky surveys. Every night, the Atlas system scans wide swathes of the sky, hunting for anything moving differently from the stars around it. Threeey Atlas immediately stood out, not just for its speed, but for its unusual trajectory. Once astronomers realised the significance of the discovery, telescopes around the world focused on this strange visitor. Every detail mattered. Scientists measured its brightness, its rotation, its shape, and even subtle colour changes, all clues to its mysterious origin. Early observations showed that Threeey Atlas was active, developing a faint coma, a halo of dust and gas, as it warmed near the Sun. This was unlike Oumuamua, which remained mysterious and tailless. In behaviour it resembled Borisov, though it was much fainter. Timing was crucial. Astronomers detected Threeey Atlas before it reached its closest point to the Sun, or perihelion, giving them a rare opportunity to observe it over most of its journey. This window allowed scientists to watch it brighten as it approached, peak, and then fade away, something they could not do with Oumuamua, which was discovered on its way out. Its perihelion occurred in late December 2019, shortly after its discovery. During this time, it became bright enough for medium-sized telescopes to gather spectroscopic data, though it was never visible to the naked eye. By early 2020, its brightness was already diminishing as it sped away, returning to the depths of interstellar space. The timeline of discovery is everything for interstellar visitors. These objects spend only a few months within observational range. Missing that brief window means losing the chance to study pristine material from another star system, a sample from another world we cannot yet visit directly. By carefully tracking Threeey Atlas, scientists also hope to understand where it came from. After being ejected from its home system, it likely drifted across interstellar space for millions of years. Its exaggerated trajectory suggests it originated in a distant region of the galaxy, though pinpointing its birthplace is difficult due to the gravitational influences of nearby stars. Still, every observation offers clues about which star nurseries might have launched it on this incredible journey, giving humanity a fleeting but priceless glimpse of truly alien matter. Why the name Threeey? Let's find out. Threeey Atlas is much more than just a name. It carries a story, a record of discovery, and a signal that this object is truly extraordinary. Its name tells us where it was first seen, how it is classified, and most importantly, how it stands apart from the countless comets and asteroids that orbit our Sun. The I in its name is what sets it apart. Unlike the letters used for ordinary comets or asteroids, this single letter marks Threeey Atlas as something rare. An interstellar object, a traveller born around a distant star, wandering freely across the galaxy and briefly passing through our solar neighbourhood. The convention of adding an I for interstellar objects began only recently. Before 2017, no confirmed interstellar visitors had ever been recorded, so there was no naming system for such wanderers. That changed with the discovery of Oumuamua in 2017. Once astronomers confirmed that Oumuamua was travelling on a hyperbolic unbound path, meaning it would never return, the International Astronomical Union, or IAU, decided that objects from beyond our solar system deserved their own special classification. That is how the I designation was born, standing simply for interstellar. Numbers are assigned in order of discovery. The first confirmed interstellar object, Oumuamua, received the designation 1I. The second, Comet Borisov, discovered in 2019, was assigned 2I. Now, Threeey Atlas officially holds the title of the third, confirmed interstellar object ever observed. Each new detection adds the next sequential number, 4I, 5I, and so on. This straightforward numbering system forms a historic catalogue, documenting a small but growing collection of alien visitors drifting through our solar system. The second part of the name, Atlas, honours the telescope survey that first spotted it, the Asteroid Terrestrial Impact Last Alert System, or ATLAS, based in Hawaii. ATLAS was originally designed to detect asteroids that might pose a threat to Earth. Its automated telescopes sweep the night sky every evening, searching for anything that moves against the backdrop of stars. In December of 2019, these telescopes spotted Threeey Atlas as a faint, fast-moving point of light. At first, astronomers thought it was just another distant comet, but careful observations soon revealed something remarkable. Its orbit was hyperbolic, confirming that it came from beyond our solar system. Including the survey's name in the object's designation is a common tradition. It recognises the team and the technology that made the discovery possible, while also giving astronomers and the public an easy way to link the object to its origin. In this case, the ATLAS system not only found the object, but did so early enough for detailed follow-up observations, making its inclusion in the name even more meaningful. Why all the attention on the I designation? Because it separates these visitors from anything formed under the Sun's influence. Ordinary comets are labelled with a C, and asteroids with a number or an A, but interstellar objects are fundamentally different. They are cosmic time capsules, carrying materials forged in alien star systems and shaped by processes entirely independent of our own. The I instantly tells scientists that what they are studying comes from far beyond the reach of the Sun. This designation also sparks scientific excitement. Each interstellar visitor is a rare opportunity to study how other planetary systems form and evolve. While spacecraft can reach only a few objects in our own solar system, interstellar objects come to us, bringing with them untouched ices, dust, and possibly even complex organic molecules. Observing them can reveal the chemical fingerprints of distant stars, offering priceless clues about the diversity of planetary systems across the Milky Way. The name of Threeey Atlas also reflects how quickly this field is expanding. In 2017, no interstellar objects had been confirmed. Just a few years later, we now have 3. That may seem modest, but it suggests that such cosmic travellers are far more common than once believed. Older surveys simply could not detect them because they were too faint. The arrival of Threeey Atlas hints that we are entering a new era of discovery, especially with advanced telescopes like the Vera Rubin Observatory and its Legacy Survey of Space and Time, or LSST, which may uncover dozens or even hundreds of interstellar visitors in the decades ahead. For scientists, the sequential numbering also creates a historical record of interstellar exploration. In the future, astronomers will look back at 1i, 2i and 3i as the pioneers of a completely new branch of astronomy. Each number is more than a catalogue entry. It is a milestone, a marker of humanity's expanding understanding of the galaxy. 3E Atlas is far more than a clever name. It acknowledges that this icy traveller belongs to a brand new historic category, reshaping our understanding of how material moves between stars and how planetary systems form. Every interstellar object is a message from a distant part of the galaxy, and Threeey Atlas is the latest chapter in this extraordinary story. Its name is both a record of discovery and a reminder that the universe is far bigger and more interconnected than we ever imagined. Where did Threeey Atlas originate from? Every interstellar object carries a story etched into the path it traces through space, a tale of violent ejections, wandering stars, and the ancient history of our galaxy. Astronomers are racing against time to decode that story for Threeey Atlas before it slips forever into the vast emptiness beyond our solar system. Where did this extraordinary visitor originate? That is the mystery at the heart of their quest. If scientists can determine its birthplace, or even just narrow down the regions of the Milky Way it once called home, they could unlock secrets of the galaxy's distant past. The journey to uncover its origin begins with orbital reconstruction. When Threeey Atlas, officially named Threeey Atlas, was first observed, astronomers calculated its unusual trajectory, a hyperbolic orbit, unbound to the Sun. This immediately confirmed it as a true interstellar traveller. Unlike elliptical orbits, which loop repeatedly around the Sun, a hyperbolic orbit shows that an object is merely passing through, tugged slightly by the Sun's gravity but never trapped. By tracing this orbit backward in time, scientists can estimate the direction from which it entered the solar system and make predictions about its path through the galaxy. Interstellar objects like Threeey Atlas can drift across space for millions, sometimes billions of years. Over such vast times, even tiny gravitational nudges from nearby stars, massive molecular clouds or wandering planets can dramatically change their trajectories. For Threeey Atlas, astronomers have reconstructed a rough incoming direction, pointing to a broad patch of the sky. But pinpointing a single birth star is nearly impossible without perfect knowledge of all past interactions. Current models suggest that Threeey Atlas may have come from regions in the Carina or Scorpius constellations, areas rich in star-forming activity. These stellar nurseries are bustling with massive clouds of gas and dust, where new stars and planets are born. Interstellar objects are believed to originate from such environments. During the early stages of planetary system formation, gravitational interactions, especially with giant planets, can hurl comets, asteroids, and other small bodies out of their home systems entirely. Once ejected, these objects drift through interstellar space as true galactic wanderers. For Threeey Atlas to reach our solar system, it may have been travelling for tens of millions of years, or even longer. Unlike comets formed in our solar system, which follow predictable orbits, interstellar objects roam freely, their paths shaped by the gravity of passing stars. Some computer simulations even suggest that before arriving here, Threeey Atlas may have slipped through other star systems, each flyby subtly altering its trajectory. These encounters could have warmed its surface slightly or added fresh dust, leaving behind chemical fingerprints that astronomers are now trying to decipher. Tracking its exact origin is complicated because the galaxy is always in motion. Stars drift, spiral arms rotate, and stellar orbits are tugged and twisted by the gravity of giant clusters. Rewinding the journey of Threeey Atlas over tens of millions of years inevitably introduces significant uncertainty. Even with precise measurements of its current speed and orientation, the further back scientists trace, the less definite the results become. Most interstellar objects are thought to begin life as victims of planetary ejection events. In young systems, giant planets, like Jupiter in our solar system, often act as gravitational slingshots, launching comets and icy bodies into the vast emptiness between stars. Some debris may even be expelled violently by collisions or close stellar encounters. Threeey Atlas might be a fragment of a shattered exoplanet or a leftover piece of a young system's protoplanetary disk. Studying its composition offers additional clues to its birthplace. If it is rich in carbon monoxide or carbon dioxide ices, it probably formed in the frigid outer regions of its home system, similar to our Kuiper belt or Oort cloud. If it contains silicate material, it may have originated closer to its parent star, in a warmer asteroid-like region. Early spectroscopic observations indicate that Threeey Atlas is coated with volatile ices, suggesting a distant cold formation zone. Its faint comet-like activity, a delicate halo of gas and dust, hints that its interior may still hold pristine, untouched material. This makes it a cosmic time capsule, preserving conditions from its place and era of birth. Comparing its composition to previous interstellar visitors like Oumuamua and Borisov could reveal whether it shares a common origin or comes from an entirely different stellar nursery. The hyperbolic orbit of Threeey Atlas is the clearest proof that it is not from our solar system. Unlike planets and comets trapped in elliptical or circular paths around the Sun, this object moves on a trajectory that ensures a single fleeting visit. Its orbit tells the story of its interstellar origin with mathematical certainty. Objects formed within our solar system are bound by the Sun's gravity, looping repeatedly over millions or billions of years. Even the most distant comets of the Oort cloud are caught in elongated ellipses, returning after thousands of years. A hyperbolic path, however, is fundamentally different. It is a one-way ticket confirming the traveller was born elsewhere. For Threeey Atlas, astronomers measured an orbital eccentricity, a number that defines the shape of its orbit, greater than 1. Values below 1 indicate an ellipse, exactly 1 is a perfect parabola, and values above 1 confirm a truly hyperbolic orbit, guaranteeing escape into interstellar space. This single number alone marks it as a true cosmic wanderer, a messenger from a distant world. The measured orbit of Threeey Atlas is highly unusual. Its eccentricity, a measure of how stretched out an orbit is far above 1. This leaves no room for doubt. It did not originate from within our Sun's gravitational domain. Its speed tells the same story. Long before it ever drew near to the Sun, Threeey Atlas was already moving at velocities far too great to belong to a native comet from our solar system, even one nudged inward from the distant Oort cloud. For context, comets that are born in our solar system, even when gravitationally nudged by giant planets like Jupiter or Saturn, typically drift at speeds of just a few kilometers per second relative to the Sun when they are far away. By contrast, Threeey Atlas entered our solar system already travelling at interstellar speeds, tens of kilometers per second, proving it had been roaming freely through the galaxy long before it reached us. As it approached the Sun, solar gravity pulled on it, briefly accelerating the object as it passed through the inner solar system. Once it moved away from the Sun, it slowed again. But even after accounting for this gravitational push and pull, its outbound speed remains far above the solar escape velocity. In other words, it was never gravitationally bound to our Sun. Astronomers also compared its incoming direction with models of comets originating from the Oort cloud. Occasionally, comets from our solar system can be nudged onto slightly hyperbolic paths by close encounters with planets, but these near-parabolic trajectories barely rise above an eccentricity of 1. Threeey Atlas, however, follows an orbit far more extreme than anything explainable by planetary interactions alone. The only plausible explanation is that it came from interstellar space. Studying its orbit does more than confirm its extraterrestrial origin. It offers clues about its long journey. By carefully retracing its path through space, scientists can estimate how long it has been travelling. Current theories suggest that it may have been ejected from its home star system during the chaotic early years of its formation, and has been wandering the galaxy for tens of millions of years. The strong gravitational forces that originally flung it into interstellar space are preserved in its hyperbolic orbit, making it a kind of fossil relic of that dramatic ejection. Its motion also differs in fascinating ways from the two interstellar objects previously discovered. The first, Comet Borisov, behaved much like a normal active comet, showing a visible tail of gas and dust. The second, Oumuamua, tumbled oddly and displayed no obvious tail at all. Threeey Atlas sits somewhere in between. In terms of its unusually high excess speed, it resembles Oumuamua, but its orbit and faint coma are more like Borisov's. This growing variety gives astronomers a tiny but steadily expanding sample of interstellar visitors, hinting that such objects can come from a wide range of star systems and be ejected through many different processes. So how fast is Threeey Atlas actually travelling? One of the clearest signs that Threeey Atlas is not from our solar system is its incredible speed. Objects that form within our Sun's family rarely reach velocities high enough to break free from the Sun's gravitational grip. Yet, Threeey Atlas did just that. Its motion tells the story of a violent ejection from another star system, and a long, lonely journey across the void of interstellar space. This was no gentle escape. Threeey Atlas didn't merely drift away. It surged forward with a force far beyond anything normally seen among comets and asteroids in our solar system. When astronomers measured its motion, they found that even before it felt the Sun's gravity, Threeey Atlas was already hurtling toward our solar system at speeds of roughly 26 to 30 kilometers per second relative to the Sun. To put that in perspective, most comets born within our solar system, even those from the distant Oort cloud, travel at only a few kilometers per second when they are far from the Sun. What sets Threeey Atlas apart is its hyperbolic excess velocity, the speed it will continue to carry even after leaving the Sun's gravitational pull. This is the unmistakable signature of a visitor that is truly unbound, a traveller with no intention of returning. As it drew closer to the Sun, Threeey Atlas accelerated under the Sun's gravity, reaching astonishing velocities when it passed through its closest point, or perihelion. Estimates suggest that at this moment it exceeded 60 kilometers per second, racing through the inner solar system before swinging back outward. Once it drifts beyond the Sun's reach, it will return to its original interstellar cruising speed, silently wandering the galaxy once more. But why does this speed matter so much? The answer lies in how objects gain their motion. Objects that form in the solar system are born with energies tied to the Sun's gravity. Even comets from the distant Oort cloud, nudged inward by passing stars or massive planets, still eventually return to their long elliptical orbits. While their speeds may increase near perihelion, they remain constrained by the Sun's pull. Threeey Atlas, however, arrived with far more energy than any gravitational interaction within our solar system could produce. Its extraordinary velocity tells us it must have come from far beyond, likely ejected by dramatic events in its home star system. Astronomers believe that most interstellar wanderers like Threeey Atlas are born during the chaotic early phases of planetary formation. Massive planets act as cosmic slingshots, flinging smaller rocky or icy bodies outward into space. Some are hurled outward at escape velocities never to return, while others are sent inward, colliding with their star or other planets. Over billions of years, these ejections create a population of free-floating travellers drifting between the stars, with Threeey Atlas being one of them. Its speed also provides a glimpse into the length of its journey. Travelling at 26 to 30 kilometers per second, it would take millions, or even tens of millions of years to traverse the space between star systems. There is a strong possibility that Threeey Atlas has been wandering since the earliest days of its home system, perhaps even encountering multiple star systems along the way. Each gravitational encounter subtly shifted its course and speed, guiding it toward our solar neighbourhood. Compared to the two other interstellar objects discovered before it, Threeey Atlas occupies an intriguing middle ground. Oumuamua entered our solar system at about 26 kilometers per second, while Comet Boris travelled at roughly 32 kilometers per second. All three share exceptionally high velocities, confirming that interstellar objects are typically ejected violently and move fast enough to escape their home stars forever. Its rapid transit also explains why observing interstellar objects is so difficult. They spend only a brief window within reach of our telescopes, zooming through the solar system in just a few months. By the time astronomers confirm their interstellar nature, they are often already retreating and fading from view. For Threeey Atlas, its discovery just before perihelion was a stroke of luck, giving scientists a slightly longer opportunity to study it. Even so, it brightened and dimmed rapidly, disappearing from view for most telescopes within a single year. The sheer speed of Threeey Atlas also raises the question of whether we could ever send a spacecraft to intercept such an object. With current propulsion technology, the answer is no. Capturing an interstellar visitor moving at tens of kilometers per second would require enormous amounts of energy and extremely precise timing. However, future missions might become feasible if we detect these travelers years in advance, allowing for fast-response spacecraft to prepare for interception. Interestingly, the telescope that first spotted Threeey Atlas, part of the Atlas survey, was not built to catch interstellar visitors. It was designed as a planetary defense system to detect potentially hazardous asteroids and comets that could collide with Earth. Yet in December of 2019, it achieved an extraordinary unexpected milestone, the first observation of an interstellar object as it passed through our solar system, before vanishing forever into the depths of space. The Atlas project is a remarkable astronomical initiative, developed by the University of Hawaii and funded by NASA under its Planetary Defense Coordination Office. Its mission, although simply stated, is of monumental importance: to scan the entire night sky, night after night, searching for near-Earth objects, asteroids and comets that could pose a potential threat to our planet. Atlas accomplishes this task using wide-field Schmidt telescopes, instruments specially designed to image large swathes of the sky at once. While these telescopes are not the largest or most powerful in the world, their true strength lies in their efficiency and speed at detecting objects that move across the starry backdrop. At present, Atlas operates 4 such telescopes, 2 perched high in Hawaii on Mauna Loa and Haleakala, and 2 stationed in the southern hemisphere, one in Chile and another in South Africa. Each of these telescopes sweeps the skies multiple times each night, automatically flagging any object that shifts position against the relatively fixed stars. Most of the time, these moving points of light turn out to be ordinary main belt asteroids or comets already known to astronomers. But occasionally something extraordinary appears, an object moving faster than usual, or on a trajectory unlike anything seen before. That is exactly what happened on December 12, 2019, when Atlas detected a faint object that moved slightly faster than the typical comet. Initially, astronomers assumed it was just another ordinary comet travelling in from the outer reaches of the solar system. It was catalogued under the provisional designation C2019Y4 Atlas. However, as days passed and more observations poured in, something unusual became clear. Its orbit did not resemble that of a long-period comet. Preliminary calculations indicated a hyperbolic path, with an eccentricity exceeding 1. This immediately drew the attention of astronomers around the globe because such hyperbolic orbits are almost always associated with objects that come from beyond our solar system. Over the following weeks, careful observations refined its trajectory, revealing the astonishing truth. This was not a normal comet at all. It was an interstellar visitor, the third confirmed object of its kind ever detected. Following Oumuamua and Tui Borisov, this remarkable visitor received its official designation as Threeey Atlas. The timing of Atlas's discovery made it even more extraordinary. Both Oumuamua and Borisov had been detected relatively late in their journeys. For instance, Oumuamua was only spotted after it had already passed perihelion and was speeding away from the Sun. In contrast, Atlas detected Threeey Atlas before it reached its closest approach to the Sun, granting astronomers precious additional weeks to study it while it brightened as it drew nearer. This early detection enabled detailed follow-up observations, including spectroscopy, light curve analysis, and preliminary attempts to estimate its composition. The Atlas telescopes are ideally suited for such discoveries because of their design for rapid, wide-field surveys. Unlike enormous telescopes that focus deeply on narrow patches of the sky, Atlas sacrifices some depth for speed and coverage, sweeping the entire visible sky every 2 nights. This makes it perfect for spotting fast-moving objects before they fade from view or vanish entirely. Once Atlas flagged the unusual object, observatories worldwide sprang into action. Hawaii's Pan-STARRS system, the Gemini Observatory, and even the Hubble Space Telescope joined the effort to monitor Threeey Atlas, recording its brightness, colour, and the activity of its tail. This international collaboration coordinated observations across multiple wavelengths, from visible light to infrared. Without Atlas's initial detection, this global scientific effort might never have happened. The discovery of Threeey Atlas also highlighted how far sky survey technology has advanced in just a few short years. Before 2017, no interstellar objects had ever been spotted, not because they did not exist, but because astronomers lacked the tools to find them. These visitors are small, faint, and move at incredible speeds, making them extremely difficult to track unless surveys cover vast portions of the sky repeatedly. Atlas's success demonstrates that with modern instruments, we are entering an era where interstellar visitors may be detected more frequently. Scientists are already rethinking the future of interstellar object detection. Next-generation surveys, such as the Legacy Survey of Space and Time at the Vera Rubin Observatory, are expected to discover many more such visitors. While Atlas, with its comparatively modest telescopes, was able to detect Threeey Atlas, the Rubin Observatory will scan the entire southern sky every few nights with its enormous 8.4-metre mirror and exceptionally wide field of view, pushing detection limits to even fainter magnitudes and earlier phases of interstellar approaches. Astronomers quickly turned to colour and reflectivity measurements, two of the most essential diagnostic techniques in planetary science, to better understand Threeey Atlas. Unlike near-Earth asteroids and comets, which can be directly sampled by spacecraft, distant interstellar visitors can only be studied through the sunlight they reflect. Every subtle shade and tiny fluctuation in brightness provides clues about the chemical composition of the object and the environment in which it formed. When first observed by Atlas and other follow-up telescopes, Threeey Atlas appeared slightly bluish-green, a hue commonly associated with comets rich in volatile ices. This suggested the presence of cyanogen or diatomic carbon in its coma, gases that glow a characteristic greenish-blue when illuminated by sunlight. Such molecules are typical of bodies formed in the cold, distant regions of star systems, where ices can survive for billions of years. The colour alone classified Threeey Atlas as an icy, volatile-rich object rather than a rocky asteroid-like one. Its albedo, or surface reflectivity, offered additional vital information about its composition and structure. Astronomers have studied the Threeey Atlas and discovered that it reflects only a tiny fraction of sunlight, somewhere around 4 to 10%, making it nearly as dark as the carbon-rich comets found in our own solar system. This faint reflection, known as low albedo, hints that its surface is covered with a thick layer of organic-rich dust or carbon-based material. These coatings likely built up over millions of years while it drifted through the vast emptiness of interstellar space, constantly bombarded by cosmic rays. High-energy radiation striking the surface can transform simple ices into more complex organic compounds, creating a dark, reddish crust that gives the object its mysterious appearance. Yet, Threeey Atlas revealed something unusual. Its brightness did not remain constant. Even beyond the expected flickers caused by typical cometary activity, the light from Atlas seemed to pulse slightly over time. These changes in its light curve suggest it has an irregular shape or a patchy surface, with some areas reflecting more sunlight than others. Some regions may still hold relatively fresh, reflective ice, exposed by recent sublimation, while other sections are covered in darker, older material that has been weathered by countless years in space. Comparing Atlas to other interstellar visitors highlights just how unique it is. Oumuamua, the first known interstellar object, displayed an unusual reddish metallic glow, likely from extreme exposure to space weathering, whereas Boris, another interstellar traveller, showed a more classic comet-like colour, resembling long-period comets from our Oort cloud. Threeey Atlas seems closer to Boris in its icy, volatile-rich composition, though its relatively weak activity suggests it may have a thicker crust of processed material, partially insulating its ices. The colour and reflectivity of Atlas tell a story of an extraordinary journey. Objects drifting between the stars endure cosmic weathering, unlike anything experienced by comets in our solar system. Over millions of years, cosmic rays, tiny meteorite impacts, and collisions with interstellar dust gradually reshape their surfaces. Dark organic films accumulate, while the ices buried deep inside remain largely preserved, shielded from the relentless radiation. The fact that Atlas still shows some active outgassing when warmed by the sun indicates that much of its interior ices have remained untouched since it was ejected from its home star system. Spectroscopic studies of sunlight reflected from Atlas have revealed water ice and carbon monoxide, two ingredients common to comets in our solar system. Yet, the balance of these compounds may differ from what we are familiar with, hinting that Atlas formed around a different type of star. For example, unusually high levels of carbon monoxide compared to water could suggest that it originated in a far colder, more distant region of its original planetary system, farther from its parent star than typical Kuiper belt objects. Scientists are carefully comparing these chemical ratios with those of known solar system comets, as even small differences can reveal whether Atlas came from a sun-like star or a cooler, smaller red dwarf. The age of Threeey Atlas as a wanderer between the stars can also be inferred from its reflective properties. If its ice were very bright, it would suggest a recent ejection, but a very dark, weathered surface points to millions or even billions of years of interstellar travel. Atlas's modest reflectivity implies a long voyage, possibly tens of millions of years, enough time to form a thick black organic layer on its surface, while preserving frozen ices deep within. Studying its reddish hue and surface gives astronomers a rare window into the past, showing how planets and comets form and evolve in distant parts of the galaxy. Each interstellar visitor like Atlas adds a piece to the puzzle of understanding how special, or common, our solar system really is. And yet, one question still fascinates everyone. Just how big is Threeey Atlas? Figuring out the size of Threeey Atlas is no simple task. Unlike asteroids or comets that are close enough for spacecraft to photograph directly, this interstellar traveller is far away, leaving astronomers to rely on indirect methods. The primary tool for gauging its size is photometry, which measures how much sunlight the object reflects. By observing its brightness and making educated guesses about how reflective its surface is, known as its albedo, scientists can estimate its diameter. Early observations suggested that Threeey Atlas is small by planetary standards, yet still considerably larger than some of the few interstellar objects discovered before it. Photometric studies indicate that its effective size lies somewhere between 60 and 120 meters across, depending on whether its surface is dark and dusty or relatively bright and icy. If its surface is coated with carbon-rich dust like many long-period comets, it would need to be closer to the upper end of that range to account for the light astronomers see. On the other hand, if fresh ice is exposed, the object could be smaller, nearer to the lower end of the range. For context, Oumuamua, the first confirmed interstellar visitor, was roughly 100 meters long, although its stretched cigar-like shape made precise measurements tricky. Comet Boris, by contrast, was much larger, with a nucleus possibly over 1 kilometer wide. Threeey Atlas sits neatly between these two extremes, closer in scale to Oumuamua, but visually more like a classic comet. Its size is also similar to that of typical comets in our solar system, hinting that interstellar comets may not differ drastically in scale from the comets born around our Sun. Threeey Atlas's brightness varies as it rotates, which tells astronomers that it is far from a perfect sphere. It may be elongated or irregular, perhaps a chunk of rock and ice ripped away from its home system. Its spin causes different surface areas to catch sunlight at different times, creating rhythmic fluctuations in its brightness, known as its light curve. These variations make pinning down its exact size even trickier, because surfaces angled toward us reflect more or less light depending on the orientation. The rarity of spotting such interstellar travellers is partly due to their small size. Even at its brightest, Threeey Atlas appeared faint and could only be seen for a brief period with moderate to large telescopes. Against the dense backdrop of the Milky Way's stars, it is remarkable that astronomers detected it at all. Had it been only half as large as it is thought to be, it might have passed entirely unnoticed. Its modest size also affects its structural integrity and survival during its interstellar journey. Tiny bodies are more vulnerable to breaking apart when they approach stars. In our own solar system, sun-grazing comets can be ripped apart by the sun's gravity and heat. Yet Threeey Atlas seems sturdy enough to withstand mild gravitational and thermal stress, though astronomers did observe subtle signs of gassing, indicating that some surface ice was slowly vaporizing, a typical comet-like behavior rather than a catastrophic disintegration. The scale of Threeey Atlas also has implications for understanding the population of interstellar objects. If it is representative of other interstellar comets, countless similar ice fragments may be scattered throughout the Milky Way. Based on statistical estimates drawn from its discovery, along with Oumuamua and Boris, billions of these icy wanderers could be drifting between the stars, many flung out during chaotic phases of planetary formation. Future sky surveys will likely uncover many more, helping astronomers understand the size distribution of these tiny travellers, even if most remain too faint to detect. However, the small size of Threeey Atlas raises questions about its origin. Is it a fragment of a larger body, like a shattered exoplanet or disturbed dwarf planet? Or was it expelled intact as a lone frozen object? Its unusual light curve and possibly elongated shape suggest the former, that it may be a piece of a larger planetary body rather than a primordial comet. Models of planetary ejection show that collisions and gravitational slingshots can hurl large chunks of debris into interstellar space, sending them on journeys across the galaxy. Whether it sports a dust tail like a classic comet or behaves differently remains an open question, but its journey and tiny scale already offer a window into the hidden world of interstellar debris, bridging the gap between planetary formation and cosmic exploration. So how does Threeey Atlas behave? When astronomers study an interstellar traveller such as Threeey Atlas, one of the first puzzles they face is whether it behaves more like an asteroid or a comet. This question is not just about labels, it reveals what the object is made of and how much frozen material or volatile substance lies hidden inside it. The difference is important. Comets, when warmed by the sun, release gases from their icy surfaces in a process called sublimation. This often creates a glowing cloud of gas and dust, known as a coma, and sometimes even a long sweeping tail that can stretch across space. Asteroids, on the other hand, are usually far quieter. They tend to be dry and rocky, reflecting sunlight but showing no clear signs of gas or dust. Threeey Atlas does not fit neatly into either group. Instead, it seems to fall somewhere in between, blurring the line between comet and asteroid. This in-between nature makes it fascinating, because it raises questions about how such interstellar objects change over the course of their incredibly long journeys between the stars. When Threeey Atlas was first spotted, astronomers noticed faint hints of activity. Careful photometric observations, measurements of how much light it reflected, revealed a thin, hazy halo around its core. This meant that some of its frozen ices were indeed melting as it drew nearer to the sun. The coma, however, was weak. It was stronger than the total silence of Oumuamua, One-Eye Oumuamua, which had no visible coma at all, but it was far weaker than the dazzling display of Borisov, Two-Eye Borisov, which produced a classic comet tail tens of thousands of kilometers long. Threeey Atlas therefore sits in a middle ground, active enough to show it carries volatile ices, but quiet enough to suggest that part of its surface is sealed under a hardened or insulating crust. The activity that astronomers detected was limited to a thin halo of dust, rather than a grand tail that swept across the heavens. This faint activity hinted at its story. One possibility is that Threeey Atlas has been drifting through interstellar space for millions of years. Over that time, cosmic rays and tiny impacts from micrometeoroids may have baked its surface, leaving behind a hardened, organic-rich crust. This shell could act like a seal, trapping deeper ices and preventing them from escaping, even when the sun's warmth reached it. Another possibility is that Threeey Atlas was never very rich in volatile ices to begin with. Perhaps it formed closer to its home star, in a region warmer than where most icy comets are born. If so, it may have contained more rocky or silicate material, with only thin traces of frozen gases remaining. Astronomers also compared how much dust it released. Borisov spewed out hundreds of kilograms of dust every second, creating a spectacular sight in telescopes. In contrast, Threeey Atlas managed only a few kilograms of dust per second at its peak activity. This weak outflow explains why it never developed the kind of sweeping tail visible even in small backyard telescopes. Yet even this faint trickle of gas and dust was scientifically valuable. By studying the light coming from the thin coma, astronomers identified traces of water vapour, carbon monoxide, and possibly carbon dioxide. These are exactly the kinds of ices that form in the cold, outer regions of planetary systems. The strong presence of carbon monoxide was especially intriguing because it suggests that Threeey Atlas was born in an extremely frigid environment, perhaps even farther from its star than the location of our own Kuiper belt. This fits with the idea that such objects are thrown out from the icy edges of young planetary systems when giant planets fling them into the void of interstellar space. The lack of a grand tail also gave clues about its inner structure. It seems likely that heat from the sun could only reach shallow depths inside its porous or fractured core, causing gases to seep out slowly rather than explosively. Its surface, reshaped over eons by radiation and countless tiny impacts, may have built up a hardened shell that protected deeper layers of ice from easy release. This raises a bigger question. Do all interstellar objects evolve in the same way, or do they follow different paths? Borisov remained rich in ices, showing dramatic activity. Oumuamua, on the other hand, showed no visible signs of gas at all. And Threeey Atlas lies somewhere in between, producing a faint halo but no tail. Perhaps some interstellar wanderers grow insulating crusts that silence their comet-like activity, while others stay relatively untouched, keeping their icy layers intact. These differences are not just curiosities, they help astronomers understand how the harsh environment of deep space reshapes icy bodies over spans of millions of years. There is also a more profound implication. The faint coma of Threeey Atlas connects to the idea of Panspermia, the theory that the seeds of life could travel between stars aboard comets. If an object can still carry organic-rich material and volatile ices after such an unimaginably long journey, then it might act as a natural courier for complex molecules. Even weak outgassing shows that these compounds can survive the brutal cold and radiation of space, only to be released again when such a traveller passes near a star. By comparing Oumuamua, Borisov, and now Threeey Atlas, astronomers are beginning to see the astonishing diversity of these visitors. Each tells a different story, and together they paint a picture of how mysterious and varied the building blocks of distant worlds can be. When astronomers discovered the first interstellar visitors, they noticed that each one seemed to carry its own unique personality. The very first Oumuamua was a mystery wrapped in silence. It did not show the usual outbursts of a comet, yet its strange acceleration hinted at hidden forces. Some scientists imagined it coated in shiny metallic hydrogen, while others thought it might be covered with an ancient biological crust. In complete contrast, the second visitor, Borisov, behaved exactly like the comets we know so well in our solar system. It was textbook in its nature, spewing out gas and dust, forming a coma, and developing a tail under the warmth of the sun. Now, standing between these two extremes is the third interstellar wanderer, Threeey Atlas. It is icy, like a comet, yet its surface seems partly sealed by an old crust that hides some of its inner activity. It is active, releasing material into space, but not in a violent or explosive way. This middle ground behaviour adds weight to an exciting idea. Interstellar objects do not all look or act the same. Instead, they likely represent a wide variety of cosmic travellers, each shaped by its birthplace, its journey across billions of years, and the harsh conditions of deep space. One of the most important things to learn about Threeey Atlas is its rotation, whether it spins smoothly, tumbles chaotically, or something in between. This may sound like a small detail, but in truth it is crucial. The way an object rotates determines how sunlight warms its surface, and in turn, where and how gas and dust escape into space. A chaotic tumble might expose hidden, volatile, rich patches every so often, causing bursts of activity. On the other hand, a steady and even spin would spread out the heating more uniformly, producing a calmer release. By studying the way Threeey Atlas rotates, astronomers can begin to uncover its inner structure, its surface behaviour, and even pieces of its long interstellar history. To measure its rotation, scientists rely on light curves. the faint but repeating changes in brightness as the object spins in space. Much like a lumpy potato reflects different amounts of sunlight as it turns, Threeey Atlas flickered with slight variations that revealed its spin. These changes were not dramatic, but they were clear enough to confirm that it is indeed rotating, and not just frozen in a static orientation. The early data suggest that its rotation takes about 9 to 12 hours to complete one turn. This pace is not unusual. Many comets in our solar system also rotate within a range of a few hours up to a full day. Its moderate spin is important. It shows that Threeey Atlas is strong enough to survive its long journey through interstellar space without flying apart, but also not spinning so fast that centrifugal forces could tear it to pieces. Yet the story does not end there. The light curve revealed something more intriguing. Instead of following a smooth, wave-like rhythm, its brightness had uneven peaks and dips. This hints that the object is probably not a neat sphere but rather stretched out or irregular in shape. It might also mean that Threeey Atlas is not spinning around a single, stable axis at all, but instead is caught in a tumbling state, what astronomers call non-principal axis rotation. Tumbling is not unusual. Small bodies in space often end up tumbling after close gravitational encounters or even tiny impacts. For an interstellar traveller, this makes perfect sense. As Threeey Atlas roamed through the galaxy for millions of years, it would have felt gentle tugs from stars it passed and may have endured collisions with tiny micrometeoroids. Over time, these little nudges can disrupt a smooth spin, sending the body into a wobbling, irregular motion. Its patchy coma and uneven dust release might also be explained by this tumbling, since sunlight would hit different regions at unpredictable times, causing uneven outbursts. If it is indeed tumbling, that also tells us something about its strength. A fragile object would likely shatter under such stresses. The fact that Threeey Atlas can endure them suggests it has enough internal cohesion, possibly held together by a tough mixture of ice and compressed dust. The rotation period also provides clues about its past encounters with stars. Each time an object passes close to a star, gases locked inside it can sublimate, creating small but repeated thrusts that gradually alter its spin. Over countless flybys, this can speed up rotation to dangerous levels, sometimes even tearing objects apart. The fact that Threeey Atlas has a moderate spin rate suggests two possibilities. Either it has only passed near a handful of stars during its long life, or its protective surface crust has kept its outgassing weak and controlled. Another possibility is that its unusual spin dates all the way back to its violent ejection from its home system. During the early days of planetary formation, giant planets often act like cosmic slingshots, throwing smaller objects into the vastness of interstellar space. Threeey Atlas may have been hurled out by the gravitational pull of such a massive world. That close encounter could have given it its current spin, preserved like a fossil record of the exact moment its cosmic voyage began. When compared with other interstellar visitors, Threeey Atlas once again seems to stand in the middle. Oumuamua clearly showed signs of tumbling and may have been extremely elongated, shaped more like a cigar. Borisov, in contrast, rotated in a more ordinary, steady manner, just as we expect from solar system comets. Threeey Atlas combines elements of both. Its spin is moderate but possibly unstable, reinforcing the idea that interstellar objects form a diverse population, each with its own story written into its rotation. Rotation is only part of the puzzle. Another powerful tool astronomers use to study such objects is spectroscopy, the analysis of light reflected and emitted by the object. By examining sunlight as it bounces off the surface or passes through the coma, scientists can identify specific atoms and molecules. Each chemical leaves a unique fingerprint in the spectrum. For an interstellar traveller, these fingerprints are like messages from another world, revealing what elements and compounds it carries and giving us a direct glimpse into the chemistry of a solar system beyond our own. When astronomers studied the spectrum of Threeey Atlas, they found something remarkable. This strange visitor from another star system looked surprisingly familiar. Its light revealed that it carried many of the same ingredients as the comets we know from our own solar system. This discovery hints at something extraordinary, that the way comets form might be a universal process, happening in star systems all across the galaxy. The clearest signal was that of water ice, recognized through faint dips in the near-infrared part of its spectrum. This was not a surprise, for water is one of the most common and widespread substances in the cosmos. It is found on planets, moons, comets, and even drifting between the stars. Its presence told astronomers that Threeey Atlas must have been born in a cold, distant region of its home system, far away from the warming glow of its parent star. But water was not alone. The comet also released volatile gases such as carbon monoxide and carbon dioxide, both of which are also common in the comets that circle our Sun. However, the exact mix of these gases varies depending on where and how a comet forms. Threeey Atlas turned out to have a little more carbon monoxide compared to water than most of the comets we know from the Kuiper belt. This suggested something fascinating. Perhaps it formed even farther out in the icy reaches of its system than our local comets usually do. Such a difference might mean that its parent star was dimmer or cooler than the Sun, forcing its icy worlds to form much farther away. Spectroscopy also hinted at the presence of complex chemicals, possibly organic molecules and hydrocarbons. These showed up as faint absorption bands in both ultraviolet and near-infrared light. Such compounds likely formed when cosmic rays battered its icy surface during its long and lonely voyage through interstellar space. This is similar to what happens to long-period comets and distant trans-Neptunian objects in our solar system, whose surfaces slowly darken and turn reddish after countless ages of radiation exposure. The detection of organic matter is especially exciting because it strengthens the idea that chemistry linked to the origins of life might be spread across the galaxy by wandering objects like this. As Threeey Atlas shed gas and dust, it was not only losing water and carbon compounds, but also scattering these organics into space. Some of these particles might one day drift into nearby star systems, eventually falling onto young planets. Over billions of years, countless objects like this could act as galactic couriers, carrying the raw ingredients of life from one system to another, seeding the Milky Way with possibilities. The data also gave astronomers a sense of how ancient and untouched its material might be. Some interstellar visitors, like Borisov, appeared to have compositions almost identical to comets from our solar system, as if they had been frozen and preserved since the day of their birth. Threeey Atlas, however, showed a slightly different story. Its surface looked processed, bearing scars from its long journey through cosmic radiation, while its deeper interior still contained fresh, unaltered ice. This layered structure, an old weathered crust hiding younger, purer ice beneath, is exactly what scientists expect to see in true interstellar travellers. Even more evidence came from the detection of silicate dust in its coma, spotted as bright peaks of infrared light. Silicates are rocky materials that condense in warmer regions close to a star. Their presence meant that Threeey Atlas was not just a ball of ice, but a mixture of both rock and ice. This suggests it may have been born in a transitional zone, somewhere between its system's hot, rocky inner worlds and its distant, icy outer belt. This supports theories that many interstellar comets are launched out into space when young planetary systems are still chaotic, mixing rocky and icy regions together in violent gravitational upheavals. Perhaps the most unexpected discovery was also the most ordinary. Aside from a few variations in gas ratios and radiation effects, Threeey Atlas contained no mysterious or exotic ingredients. In many ways, it was almost boringly familiar. But that very ordinariness carried a powerful message. It meant that the same basic chemistry that shapes comets here is likely happening everywhere in the galaxy. The implication is profound. The raw materials for planets, oceans, and perhaps even life itself are not rare, but widespread, scattered across the Milky Way, waiting to be gathered and shaped by countless other worlds. If comets that wander in from another star system look and act much like the ones that belong to our own solar family, then what sets them apart? When scientists speak of visitors from beyond our solar system, the first names that appear are 1I Oumuamua and 2I Borisov. Comparing these two trailblazers with the later arrival of Threeey Atlas is essential if we are to understand the incredible variety of these wandering strangers of the galaxy. The discovery of Threeey Atlas was only the third time in human history that astronomers had the privilege of studying an interstellar object closely. Each of these voyages carries with it a unique biography, shaped by the world it was born in, the violent event that expelled it from its home star system, and the countless ages it spent drifting alone through the deep night of interstellar space. By carefully comparing how Threeey Atlas differs from the first two, scientists hope to build a clearer picture of the kinds of raw materials that other planetary systems produce, and how those materials change over time as they wander among the stars. The most striking differences lie in how active each object is, and in how they look. 2I Borisov was unmistakably a comet. It sprouted a brilliant glowing coma and a long sweeping tail, just like the familiar comets we see in our own solar system. Its ingredients told the same story. It was made of the same kinds of frozen ices found in ordinary comets, proving that the recipe for making comets seems to be universal across the galaxy. Oumuamua, however, could not have been more different. It showed no coma, no tail, no sparkling jet of gas or dust. Instead, it looked more like a dry asteroid or a heavily weathered rock, its surface sealed by a hardened crust that trapped any remaining ices deep within. Threeey Atlas lies somewhere between these two extremes. It did show a faint whisper of comet-like activity, revealing that a little bit of its ancient ice still survived, but its fragile halo of dust and gas was so weak that it barely registered compared to Borisov's dramatic outgassing. Clearly, much of its surface had been locked away beneath a hardened shell, a crust forged during its long exile in interstellar space. Yet it was not completely lifeless like Oumuamua. Sensitive instruments still detected traces of water vapour and carbon monoxide seeping from within, a sign that untouched, pristine ices remained in its interior. The chemistry of these bodies adds another layer to the tale. Borisov's mixture was strikingly familiar: water ice, carbon monoxide and carbon dioxide in the same proportion seen in comets born in our solar system. Oumuamua's silence made it harder to study directly, but its reddish colour suggested that its surface was coated with organic material, molecules that had been baked and battered by cosmic rays over millions of years. Threeey Atlas again shows a blend of both. Its light revealed a mixture of water ice, carbon monoxide, and perhaps complex hydrocarbons, hinting that it was born in the frozen outskirts of a planetary system, but had been changed significantly by the harsh storms of interstellar radiation. The shapes and spins of these objects tell still more stories. Oumuamua was by far the strangest, with its long, cigar-like or possibly flat pancake-like form tumbling chaotically through space. Its odd behaviour even sparked wild ideas, that it might be a broken piece of a shattered planetesimal, a hydrogen iceberg, or even an alien probe. Borisov, in contrast, was completely ordinary. It had a roughly round nucleus and rotated steadily like the well-behaved comets we know. Threeey Atlas, once again, rests in between. Its brightness pattern suggests it might be somewhat elongated and even tumbling, though not as dramatically as Oumuamua. This hints that while it was jostled during its violent ejection, it managed to hold together without falling apart. Their sizes also highlight their diversity. Borisov was the giant among them, with a nucleus more than 1 kilometre wide, large enough for backyard astronomers to spot with modest telescopes. Oumuamua, in contrast, was tiny, barely 100 metres long, and would have slipped by unnoticed if not for modern sky surveys. Threeey Atlas was even smaller, measuring somewhere between 60 and 120 metres across. Its modest size explains why it was so hard to detect, and why it remained visible for only a short window of time. Why do they behave so differently? The differences in activity may reveal not only what they are made of, but also how old they are, and how long they have wandered the interstellar dark. Borisov's fresh, ice-rich nature suggests it was thrown out of its home system relatively recently, before cosmic radiation could strip it bare. Oumuamua's silence hints that it had drifted for eons, long enough to build up a thick radiation-hardened crust that sealed away its inner ice. Threeey Atlas, with its faint but still detectable activity, seems to sit in between. Weathered, yes, but not yet entirely sealed. Even their birthplaces leave behind clues. Borisov almost certainly formed in a system very much like our own, in a freezing outer region beyond giant planets where comets are naturally born. Oumuamua's exact origin is still a mystery, but its bone-dry, radiation-processed surface suggests that it might have once been part of a larger body, or formed closer to its star, in a warmer inner zone. Threeey Atlas, with its unusually high amount of carbon monoxide, points to a birthplace in an even colder environment, perhaps in the distant outskirts of a dim star system, where ices could freeze farther out. Some scientists have even asked, could it be a broken fragment of a planet? One of the most exciting possibilities about the mysterious traveller known as Threeey Atlas is that it might not be an ordinary comet at all. Instead, some scientists believe it could be something far more dramatic, a broken-off piece of a much larger world. Imagine a shard of ice and stone, once part of a planet or a moon, being ripped away from its birthplace in a violent cosmic collision and then hurled into the endless void between the stars. This idea may sound bold and speculative, yet several clues about Threeey Atlas's size, shape and chemical makeup suggest that it does not neatly fit the description of a typical long-period comet. If this bold theory is true, then Threeey Atlas would give us a once-in-a-lifetime opportunity, the chance to study raw planetary material from deep inside another solar system. It could be the fossil of an ancient moon, or perhaps even a piece of the crust of a faraway planet. The thought that interstellar space may be filled with countless such fragments of broken worlds is not at all far-fetched. The birth of planets is not a calm, orderly process. It is violent and chaotic. In the early youth of a star system, newly formed planets and moons constantly clash as they struggle to settle into stable orbits. These mighty impacts can smash entire worlds into fragments, scattering them like cosmic shrapnel. Giant planets, such as massive gas giants, add even more chaos. Their immense gravity can act like a slingshot, hurling chunks of rock and ice into the emptiness of interstellar space. Computer simulations suggest that for every planet that successfully grows into a stable world, countless smaller bodies are cast out, lost to the void during those turbulent early days. Over the course of billions of years, this violent process could fill our galaxy with trillions of wandering fragments of shattered planets and moons. Several features of Threeey Atlas strengthen the idea that it might be one of these fragments. First, astronomers noticed that its brightness rises and falls in a way that hints at an uneven, elongated shape. Unlike most comets, which are roughly rounded, Threeey Atlas seems jagged and irregular, more like broken debris than a smooth, compact cometary nucleus. Its light flickers as it spins, suggesting sharp edges, uneven surfaces, and the scars of a violent past. Second, its chemical makeup is unusual. Spectroscopic studies show that it contains both icy material and silicate dust, rocks mixed with volatiles, suggesting that it might not be a pure comet at all. Instead, it could be a fragment of a differentiated body, meaning a larger world where heavy rocky material had sunk inward and lighter, icy material had floated outward, forming separate layers. If such a body were destroyed in a catastrophic collision, a fragment like Threeey Atlas might contain both rocky crust or mantle material and deeper ices. This would explain why it behaves differently from Borisov, the interstellar comet discovered earlier. While Borisov was active and clearly full of accessible ice, Threeey Atlas shows much weaker activity. Its outer layers may be rocky or processed, hiding the ice deep below, so that less of it vaporizes when warmed by the sun. Adding to the mystery, its surface appears unusually dark, coated with carbon-rich organic material. Over millions of years, cosmic radiation can weather any interstellar object, but a planetary fragment would have started out with a much more complex mixture of rocks, ices and minerals than a simple comet. Over time, radiation would alter these materials, leaving behind the blackened crust we see today. When compared to Oumuamua, the very first known interstellar visitor, the similarities become even more intriguing. Oumuamua was also elongated, inactive, and puzzling, leading some scientists to suggest it too could be a piece of a destroyed planetesimals torn apart near its parent star. Threeey Atlas, though slightly more comet-like than Oumuamua, still seems to sit somewhere between Oumuamua's fractured stillness and Borisov's bright, icy activity. If Threeey Atlas is indeed a planetary fragment, then it must have been launched under much more violent conditions than the typical comet. While most comets are gradually nudged out of their home systems by gentle gravitational interactions, a planetary shard would require a cataclysm, perhaps a giant planet migrating inward and scattering rocky inner worlds, or even a passing star destabilizing the orbits of an entire system. Far from being rare, such events are actually thought to be common in the early lives of star systems, as many exoplanet studies now suggest. The stakes of this theory are enormous. If Threeey Atlas really is a planetary fragment, then interstellar objects are not just cosmic curiosities, They are free samples of alien worlds, fragments of planets and moons flung across the galaxy and delivered to our doorstep. By analysing their chemistry, astronomers could gain precious insight into the inner layers of planets beyond our solar system, knowledge we could never obtain by looking at their distant surfaces alone. If the mineral and ice composition of Threeey Atlas is very different from anything in our solar system, it would show us that planets around other stars may form in ways we never imagined. This possibility also touches on an even deeper question: the spread of life itself. Could such planetary fragments act as messengers between star systems, carrying the seeds of life with them? Though the odds of life surviving such a journey are extremely small, large rocky fragments could shield delicate organic molecules from radiation for millions of years. If even a single fragment survived long enough to crash onto a young habitable world, it could deliver the raw ingredients for life, a concept tied to the theory of Panspermia. Of course, proving that Threeey Atlas is a planetary fragment will not be easy. Almost everything we know about it comes from indirect observations, since we do not have physical samples to study. For now, it remains an open debate, one that future discoveries may help settle. As more interstellar objects are found, scientists may begin to notice patterns, some behaving like traditional comets, others showing signs of being fractured planetary pieces. And this raises one last question. If the galaxy is truly filled with such fragments, why do we see so few of them? It might sound surprising at first, but in all of human history, astronomers have only confirmed the existence of 3 interstellar visitors. The first was Oumuamua, the second was Borisov, and the third is Threeey Atlas. You might wonder if planets and stars all across the galaxy are constantly flinging comets, asteroids and fragments of rock into space. Shouldn't we be seeing these cosmic wanderers all the time? The truth is that interstellar objects are likely very common, but they are fiendishly hard to spot. Their rarity in our telescopes has more to do with the difficulty of detecting them than with their actual numbers in space. Several obstacles stand in our way. The first challenge is size and brightness. Interstellar objects are typically quite small, often no more than a few tens or at most a few hundreds of meters across, similar in scale to Threeey Atlas. Compared with giant planets or even large asteroids, they are tiny. Small size means they reflect very little sunlight, and to make matters worse, their surfaces have usually been darkened by long exposure to cosmic radiation. Many, like Threeey Atlas, have albedos as low as 4 to 10%, which makes them as black as charcoal. Unless they happen to come very close to Earth, or develop a bright glowing tail like an active comet, they remain almost invisible, hidden against the glittering sea of background stars. The second difficulty is speed. Interstellar objects move far faster than most comets or asteroids born in our solar system. They race through space at tens of kilometers per second, darting across the inner solar system in only a few months. By the time they are close enough to detect, they are already rushing back out into the darkness, giving astronomers only a fleeting chance to study them. Oumuamua itself was only discovered after it had already swept past the Sun, leaving scientists with just a few weeks to observe it before it disappeared. The third obstacle is sky coverage. For a long time, we simply were not looking carefully enough. Traditional astronomical surveys were designed to follow bright stars, planets and galaxies, not small, faint specks zipping across the sky. Even surveys dedicated to near-Earth asteroids like the Atlas project only scan certain parts of the sky each night, leaving huge regions unobserved. Spotting a tiny, dim, fast-moving interstellar object against a backdrop of billions of stars is like noticing a single drifting leaf in the middle of a stormy sea. Another difficulty is that these wanderers are brightest only when they venture close to the Sun. Far away, in the cold depths of space, they remain too faint to detect. Only when sunlight begins to warm their surfaces do some of them shine enough to be noticed. But even then, many remain dim. Oumuamua, for example, never developed a comet-like tail, and so it stayed faint even at its closest approach to the Sun. This means countless visitors may already have slipped through our solar system completely unseen. Yet population models suggest that interstellar objects are astonishingly abundant. Astronomers estimate that for every single star in the Milky Way galaxy, there may be trillions of icy and rocky fragments drifting through interstellar space. Most of them were likely thrown out billions of years ago, during the violent early days of planet formation, Our own solar system probably ejected countless comets and asteroids when Jupiter and Saturn migrated in their orbits. Other star systems likely did the same, filling the galaxy with wandering debris. The cosmos may be swarming with these lonely travellers, we just cannot see most of them. Even so, progress is being made. In just a little over 6 years, astronomers have gone from knowing none of these objects to discovering 3. This leap forward is thanks to powerful sky surveys such as Pan-STARRS and Atlas, which sweep the heavens every night and flag anything that moves oddly or unexpectedly. And the future looks even brighter. The upcoming Legacy Survey of Space and Time, LSST, to be conducted at the Vera Rubin Observatory, is expected to revolutionize the hunt. With its massive mirror and lightning-fast wide-field camera, LSST may discover dozens, or even hundreds, of interstellar objects every single decade. But even with this new technology, most will still escape us. Many interstellar visitors will pass far from Earth, too distant for even the most sensitive telescopes to catch. The majority are probably only a few tens of meters across, far smaller than Threeey Atlas. These miniature wanderers will glide silently through the solar system, unseen and unrecorded. Still, we can learn much from the few we do catch. One of the first clues about an object's nature comes from how its brightness changes over time. Astronomers track these changes using light curves, which reveal whether an object is smooth and round or oddly shaped and spinning unevenly. For Threeey Atlas, the brightness rises and falls in a steady rhythm every 9 to 12 hours, matching its rotation. The variations are modest, showing that it is not as extremely stretched out as Oumuamua, whose brightness swung by a factor of 10 due to its dramatic cigar or pancake-like shape. Even so, the uneven peaks of Threeey Atlas's light curve suggest a lumpy, irregular surface, perhaps scarred with ridges, craters, or fractures. A cosmic shard still carrying the marks of its long and lonely journey between the stars. An unusual or uneven shape is exactly what astronomers expect from an interstellar wanderer. Unlike big planets and moons, which are rounded into near-perfect spheres by their own strong gravity, much smaller icy and rocky objects usually keep odd, lumpy outlines. This is especially true if they are only fragments of something larger that once broke apart. Violent events such as planetary collisions, tidal disruptions near a star, powerful ejections or gravitational slingshots can smash bigger worlds or planetesimals into sharp-edged shards that are then cast out into the dark of interstellar space. The oddly shaped body of Threeey Atlas may therefore carry scars from a turbulent and violent past, perhaps tied to the very moment it was thrown out of its home star system. Its irregular brightness, which rises and falls as it spins, offers more clues. The size of this brightness variation suggests not only the object's shape but also the nature of its surface. Imagine one side of the body darkened by ancient radiation-processed material, while the opposite side glitters with patches of fresh reflective ice. Such a mixed surface, where shiny new volatiles lie beneath an older weathered crust, has already been hinted at by spectroscopic studies. The patchiness of the surface is likely the reason its brightness curve looks irregular rather than smooth. Interestingly, the variation in brightness is not extreme but moderate. This might mean that Threeey Atlas has, over millions upon millions of years, slowly lost some of its jagged edges. Tiny but constant impacts with micrometeoroids, along with the gradual sublimation of exposed ice into gas, would have worked like a cosmic sandpaper, rounding its shape a little. Yet it's still far from smooth. It shows no signs of ever being reshaped by processes such as melting, internal heating, or geological activity. It remains what it is, a small, inactive traveller from another star, scarred but enduring. When astronomers compare its shape to the other 2 interstellar visitors, the differences become clear. Oumuamua, the first known object, had a very strange, elongated form, so unusual that some scientists wondered if it might be the fragment of a larger shattered body, or even a fragile slab of exotic material, like a hydrogen iceberg folded in on itself. By contrast, 2I Borisov behaved like a textbook comet from our own solar system. Its nucleus was fairly round, and its brightness showed little to no variation, making it seem far more ordinary. Threeey Atlas, however, rests between these 2 extremes. It looks less like a whole comet nucleus and more like a shard of ice torn from a bigger frozen body. It is irregular, yes, but not alien or unexplainable. The shape also decides how the object reacts to sunlight. A body that is lopsided heats unevenly. Some patches covered with a crust may stay dormant, while others where fresh ice is exposed can suddenly erupt with jets of gas. These eruptions may burst from just a few active spots, pushing against the body like miniature rocket engines. Over long timescales, such jets can alter the spin of the object, introducing small torques that make it wobble or slightly change its rotation speed. The faint irregularities seen in Threeey Atlas's light curve may be explained by this quiet tug-of-war between heat, ice, and gas. But there is another question. Does its uneven shape make it fragile? Compared with solid, spherical bodies, jagged shards often lack the same structural strength. If Threeey Atlas were ever to pass too close to a star or be caught in the crushing grip of tidal forces, it could break apart more easily than a solid, compact world. Yet its very survival during its passage through our solar system shows that, despite its irregularity, it is still tough enough, compact and cohesive enough to endure moderate heat and gravitational stresses. Even so, much remains uncertain. Because Threeey Atlas is so faint, astronomers struggle to extract fine details of its outline. They continue to refine their models of its shape by combining photometric measurements, the study of its changing brightness, with calculations of its rotation period. Still, the limits of current instruments mean much about its form remains hidden. In the future, however, powerful next-generation telescopes such as the Vera C. Rubin Observatory may finally reveal the shape of such interstellar objects with far greater precision. With those clearer views, humanity may one day piece together not only what these wandering fragments look like, but also the deeper stories of their violent births and long journeys between the stars. So which star system might have thrown it out into space? Finding the exact birthplace of Threeey Atlas is one of the greatest puzzles in modern astronomy. Once an object is thrown out of its home star system, it begins a lonely and uncertain journey that can last for millions or even billions of years. Along the way, the object is constantly nudged and pushed by the pull of the Milky Way's immense gravitational field, by the passing tug of wandering stars, and by the invisible force of gigantic clouds of gas and dust drifting through space. These endless influences gradually twist and reshape its path, making it nearly impossible to trace its origins with certainty. Yet astronomers do not give up so easily. By carefully retracing the object's hyperbolic orbit, the open-ended curve it followed into our solar system, they can at least narrow down the regions of space it might have come from. When Threeey Atlas was first spotted, astronomers quickly calculated the direction from which it was approaching. Its path seemed to point roughly toward the skies near the constellations Carina and Scorpius, two dazzling regions that are rich with stellar nurseries, vast clouds of gas and dust where new stars and planets are born. These areas are natural candidates, because in the turbulent youth of such systems, massive gravitational disturbances often hurl out comets, icy fragments, or even pieces of entire planets into the darkness between the stars. One strong possibility is that Threeey Atlas was flung from a system much like our own, orbiting a young sun-like star surrounded by massive gas giants. In such systems, the giant planets roam through the early protoplanetary disk, scattering smaller icy and rocky bodies in every direction. Some of these unfortunate wanderers are pulled into the star, others smash into larger planets, while a few gain enough speed to break free entirely and are cast into the galaxy. Over time, such expelled fragments can become lonely travellers like Threeey Atlas, doomed to drift endlessly from one star field to another. The fact that its chemical makeup includes water ice and carbon monoxide, substances common in the colder outer regions of star systems, supports this idea. But there is another contender, the humble red dwarf star system. Red dwarfs are the most common type of star in the Milky Way, and many are believed to possess thick belts of icy material. Because red dwarfs are smaller, cooler and dimmer than stars like our Sun, their icy zones and habitable regions lie much closer in. This means that planets wandering through their systems, or the close gravitational encounters of neighbouring stars, could easily fling icy bodies out into interstellar space. Interestingly, The unusually high amount of carbon monoxide found in Threeey Atlas hints that it may indeed have formed in such a colder environment around a dimmer, cooler star. Even so, tracing it back to one exact star is nearly impossible. The Milky Way is always in motion. Stars orbit the galactic centre at different speeds, changing their positions dramatically over tens of millions of years. By the time Threeey Atlas arrived at our doorstep, its original path had almost certainly been twisted by countless gravitational encounters. Even though its trajectory seems to point toward Carina or Scorpius, the star, or stars, that once gave it the final push might no longer be anywhere near that part of the sky today. Still, astronomers try. With the help of missions like Gaia, which maps the positions and movements of billions of stars with extraordinary precision, researchers run simulations backward in time. These models search for stars that may have passed close to the predicted path of Threeey Atlas millions of years ago. But the further back they go, the fuzzier the results become. So far, no single star has been identified beyond doubt as the birthplace of this wandering visitor. The way in which it was ejected also provides clues. Most interstellar objects are believed to be cast out during the earliest, most chaotic stages of planetary system formation, usually within the first 100 million years of a system's life. If Threeey Atlas was born inside a crowded young star cluster, where neighbouring stars often pass close to each other, then the chances of it being thrown out would have been even higher. In such places, close stellar flybys can easily destabilise planetary systems, launching comets and fragments into the galaxy at escape speed. If this was the case, Threeey Atlas may have been expelled very early in its system's history, and then spent tens of millions of years drifting alone through the Milky Way, before finally arriving here. Even its surface tells a story. The dark, carbon-rich crust covering Threeey Atlas suggests it has been wandering for an extraordinarily long time. Constant exposure to cosmic rays slowly alters the chemistry of an object's surface. Freshly ejected bodies often keep brighter, younger-looking surfaces, while those that have been adrift for tens or even hundreds of millions of years grow darker and more processed. This evidence hints that Threeey Atlas was expelled long ago, perhaps even during the earliest days of its home system. Could it have carried with it the building blocks of life, organic molecules from another star system? Dark. One of the greatest puzzles surrounding Threeey Atlas is whether it carries organic molecules, the basic chemical ingredients needed for life. This question excites scientists because if the answer is yes, then Threeey Atlas is not merely a frozen wanderer from another star system, but a potential messenger of life's building blocks. Organic molecules are carbon-based compounds, and they are the foundation for more complex substances like amino acids, nucleic acids, and proteins, all of which are essential for living things. If interstellar travellers such as Threeey Atlas carry these molecules, then they may play a vital role in spreading the chemistry of life across the galaxy. This supports a fascinating idea known as Panspermia, the theory that the raw materials of life drift between stars on natural carriers like comets, asteroids, and planetary fragments. Careful study of the light spectrum reflected by Threeey Atlas suggests strongly that it does indeed contain organic compounds. Astronomers have noticed a faint green glow in its surrounding coma, the hazy envelope of gas and dust that forms when a comet warms as it nears a star. This greenish colour is caused by the presence of cyanogen and diatomic carbon. Both of these substances are commonly seen in active comets, and usually come from the breakdown of larger carbon-rich molecules when sunlight strikes the surface. This means that beneath the glow lies a nucleus covered in a coating of complex organic matter. Similar types of organics have been discovered on comets within our own solar system. They are widely believed to be the precursors of life's molecules, the early steps in forming amino acids and nuclear bases, which are the letters of DNA and RNA. This makes Threeey Atlas even more important, as it shows that the same chemical processes happening here may also be common in faraway planetary systems. The surface of Threeey Atlas is also unusually dark, reflecting very little light. Its albedo, or reflectivity, is only between 4 and 10%, which is typical of comets coated in tholins. Tholins are reddish-brown organic solids that form when ultraviolet radiation and cosmic rays strike simple ices such as methane and nitrogen. Over millions of years drifting through the emptiness of interstellar space, Threeey Atlas would have been constantly battered by high-energy radiation, slowly building up thick crusts of these organics. This outer layer acts like both a shield and a diary. It protects the inner ices from further damage, while also recording the long chemical history of the object's journey. These findings are remarkable because they demonstrate that organic chemistry is not unique to our solar system. If Threeey Atlas was born around another star yet developed the same kinds of carbon compounds as our own comets, then prebiotic chemistry may be a normal feature throughout the Milky Way. In young star systems, tiny ice grains coated in organic material often form in the cold outer regions of the spinning protoplanetary disks, the nurseries of planets. These grains eventually clump together into comets and planetesimals. Later, if these bodies collide with young planets, they can deliver their treasure of organics, possibly helping to kickstart life. The inside of Threeey Atlas is thought to be even more pristine than its weathered surface. Scientists believe its hardened crust, forged by cosmic rays, may only be a few meters thick. This relatively thin shell would have shielded the inner ices for billions of years, preserving them much as they were when Threeey Atlas first formed around its parent star. Deep within, the untouched ices may hold fragile molecules such as methanol, formaldehyde, and simple precursors of amino acids. If one day humanity could sample material from its core, we might recover a frozen snapshot of the chemistry that existed in another star system long before our own Earth was born. This leads to a profound and almost poetic thought. Objects like Threeey Atlas are not just visitors, they are messengers from other suns. As they approach stars, solar radiation can drive out some of their ice and dust into space. These fine, organic-rich particles may then wander through the galaxy for millions of years, until they eventually collide with a planet in another system. Laboratory experiments on Earth have shown that many organic molecules are tough enough to survive these long, harsh journeys if protected by ice or rock. Life itself may not withstand the voyage, but the seeds of life, the essential chemistry, very likely can. Even the very existence of Threeey Atlas proves something profound. Planetary systems do not keep all their material to themselves. Instead, they regularly fling comets, fragments, and planetesimals into interstellar space. There are likely billions of such objects drifting across the galaxy. If only a small fraction of them carry organics, then the Milky Way is constantly exchanging life's building blocks between stars. This would dramatically increase the chances that life appears wherever the right conditions exist. Which planets gave Threeey Atlas the final gravitational push that sent it our way? The journey of Threeey Atlas through our solar system was anything but straightforward. Like a traveller wandering through a crowded marketplace, its path was nudged and tugged by the invisible hands of gravity. The most powerful of these hands belonged to the great planets, especially Jupiter and Saturn, whose immense masses exerted subtle but important influences on its flight. When Threeey Atlas first swept into our solar system, its path was already set in the shape of a hyperbola, meaning it was not circling the Sun like an ordinary comet or asteroid, but instead just passing through. However, astronomers know that this kind of path is not completely unchangeable. The gravity of huge planets can act almost like a cosmic steering wheel, giving a passing object a small push or a twist in direction. These small adjustments in speed and angle can teach scientists a lot about both the object itself and the mighty forces at work in our solar neighbourhood. As soon as the Atlas survey team detected Threeey Atlas, they quickly measured its speed and incoming trajectory. Once it was confirmed to be an interstellar visitor, astronomers began carefully tracking every step of its passage, watching to see if the planets it passed near would alter its course. Unlike the comets and asteroids that stay trapped by the Sun's gravity in neat elliptical or circular orbits, Threeey Atlas was racing so fast that it could not be captured. Its hyperbolic track made it clear that this was only a brief visit. Still, that did not mean it would ignore the pull of the solar system's giants. Jupiter, the king of the planets, is especially famous for its gravitational slingshot effect. With a mass more than twice that of all the other planets combined, Jupiter's gravity can fling space rocks and comets onto entirely new paths, sometimes hurling them out of the solar system altogether or sending them plunging inward toward the Sun. For Threeey Atlas, however, the encounter was not nearly so dramatic. Because its closest approach to the Sun, its perihelion, was still far away from Jupiter's position, the giant planet's influence was more of a gentle nudge than a powerful shove. it may have tilted the object's direction slightly, or given it a tiny boost in speed, but nothing compared to the sweeping changes Jupiter has caused for comets that wandered closer. Saturn, the second largest planet in the solar system, and the one famous for its shimmering rings, may have played a more noticeable role. Threeey Atlas's path brought it nearer to Saturn than to Jupiter, and although the distance was still vast, Saturn's heavy mass allowed its gravity to extend far enough to tug on the interstellar visitor. Much like Jupiter, Saturn could not capture the comet or force it into orbit, but it might have added its own subtle adjustment to the already complex trajectory. In fact, the faint but measurable changes in the object's speed and angle hint that one or both of these gas giants left a quiet but lasting mark on its journey. Even so, when astronomers compared their observations with the calculations, they were struck by how steady the motion of Threeey Atlas remained. Despite the enormous gravitational pull of both Jupiter and Saturn, its hyperbolic orbit hardly changed. This proved that it was never bound to the Sun in the first place. It was an interstellar traveller on its own path, and the planets of our solar system were no more than passing bystanders. This story of near encounters with the giant planets raises a fascinating question. How many other interstellar wanderers might have passed through our solar system unseen? 3. I-Atlas was small, faint, and only discovered thanks to the watchful eyes of the Atlas survey. If such objects are common, as many scientists suspect, then dozens, perhaps even hundreds of similar interstellar fragments could be racing past us at this very moment. Most would be too dim or inactive for our current telescopes to detect. Some may be flung away by Jupiter's mighty gravity, while others slip quietly through, leaving behind no sign that they were ever here. Is there any chance that it might threaten Earth or the solar system? When astronomers first realised that Threeey Atlas was not just another comet or asteroid from our own solar system, but a true visitor from the stars moving at incredible speeds, a natural question immediately arose. Could this strange traveller pose a danger to Earth? The answer, fortunately, is a clear no. Threeey Atlas is rushing through space so quickly that it never had any chance of colliding with our planet. In fact, just like the other known interstellar wanderers, its path ensures that it will not even come close. This is because Threeey Atlas follows what scientists call a hyperbolic trajectory, a flight path that is not curved into a loop by the Sun's gravity, but rather one that lets it pass through the solar system only once before it escapes forever into the vastness of interstellar space. It is a one-time visitor, never to return. Even when it came closest to the Sun, at the point called perihelion, the object never approached the inner solar system where Earth, Venus and Mars orbit. Instead, its nearest distance to the Sun was about 0.3 astronomical units, which equals roughly 45 million kilometers. To put this into perspective, this is about the same distance as the orbit of Mercury, the innermost planet of the solar system. Earth, by comparison, is one full astronomical unit away from the Sun, more than 3 times farther out. This means that Threeey Atlas remained far beyond Earth's neighbourhood, gliding through space without threatening any planet. Even if its course had been slightly different, its breathtaking speed would have protected us from danger. At its fastest, Threeey Atlas was moving at around 60 kilometers every second, nearly 10 times faster than a typical comet from our solar system. At such an extreme velocity, it would have passed by any planet before gravity could have a chance to pull it into an orbit or capture it. This incredible speed alone guarantees that the chance of a collision was practically zero. Astronomers carefully calculated the minimum approach distance, the closest it could possibly come to Earth or any other world, to confirm that there was no risk. These calculations are not only important for planetary defense, but also for improving our understanding of how interstellar objects behave when they sweep through our solar system. Interestingly, while Threeey Atlas never came anywhere near Earth, it did pass closer to the giant planets Jupiter and Saturn. These enormous gas worlds, with their powerful gravitational fields, gave the traveller a few subtle tugs as it moved by. Though these nudges were not strong enough to alter its overall journey, they did bend its path slightly, like a breeze shifting the course of a leaf drifting through the air. Studying these gravitational encounters helps astronomers refine their models, making future predictions about incoming interstellar objects more accurate. Even though Threeey Atlas will soon vanish back into the darkness of space, Leaving the solar system forever, its brief visit has already provided important lessons. It reminds us that the cosmos is filled with high-speed travellers, many of which may pass much closer in the future. The next one might not be as distant. That is why astronomers stress the importance of detecting these objects early, long before they reach their closest approach. Today, new observatories such as the Vera C. Rubin Observatory, along with next-generation sky surveys, are preparing to scan the heavens more thoroughly than ever before. With these powerful eyes on the sky, we may detect many more of these rare visitors from other star systems, giving us the time we need to study them and understand their behaviour. For now, Threeey Atlas stands as only the third confirmed interstellar object ever found. But as technology improves, discoveries like this may become far more common. Its safe passage shows that not all interstellar wanderers are dangerous, but they remain fascinating messengers from the greater galaxy, carrying with them the secrets of worlds beyond our own. For how much longer will Threeey Atlas remain visible to our telescopes before it slips back into the darkness of space? One of the most fascinating yet frustrating things about studying Threeey Atlas is just how short the time window is during which it can be seen. Ordinary comets and asteroids that belong to our solar system often remain visible for many years, sometimes even for decades, circling the Sun again and again. But interstellar wanderers like Threeey Atlas are very different. They appear suddenly, race across the inner solar system, and then vanish forever into the depth of the galaxy. Their strange, exaggerated paths ensure that once they have passed by, they will never return. This creates a unique problem for astronomers. They must act with incredible speed, because every day, every hour, and sometimes even every minute matters. If they hesitate, the chance to study such an object is gone forever. When Threeey Atlas was first detected by the Atlas survey in December of the year 2019, it was already moving at astonishing speeds. Right away, astronomers realized that this was no ordinary visitor. Unlike other comets, which might return after thousands or even millions of years, this one was on a one-way journey. Its visit was a once-in-a-lifetime event, and the opportunity to study it was shrinking rapidly with each passing day. At the moment of its discovery, Threeey Atlas was still hundreds of millions of kilometers from the Sun. As it drew closer, sunlight began to heat its surface, causing ice and gas to escape and form a faint glowing cloud around it, known as a coma. This made the object brighter and easier to spot, but only for a short while. Its brightness reached its highest point just before perihelion, the moment when it came closest to the Sun, in May of the year 2020. After that, as it moved farther away, its light began to fade. The Sun's heat stripped away its halo of dust and gas, leaving it dimmer and harder to detect. The brief period during which Threeey Atlas could be studied made every single observation precious. In total, it was visible from Earth for only a few short months. Because of this, astronomers had to coordinate telescopes all around the world, racing against time to collect as much information as possible. Only the most powerful observatories with the most sensitive instruments were able to track it in detail, because the object was so faint and distant. In the future, facilities like the Vera C. Rubin Observatory, which will soon begin scanning the skies with unmatched speed and precision, will help scientists spot these fleeting interstellar travellers earlier. But when Threeey Atlas was discovered, its short time in the spotlight was already nearing its end. The story of Threeey Atlas is a vivid reminder of just how fleeting discoveries of interstellar objects can be. They move so quickly and travel such enormous distances that astronomers often have only a matter of months, or even weeks, to study them before they vanish forever. In the case of Threeey Atlas, researchers had only a narrow window of time to measure its path, study its chemical makeup, and observe its activity. After perihelion, its brightness declined sharply, and it soon disappeared into the blackness of space. This challenge is not just about scientific curiosity, it also affects planetary safety. Although interstellar objects like Threeey Atlas travel so fast that the chances of one striking Earth are extremely small, detecting them is still crucial. By studying them carefully, scientists can better understand how often they appear, how they behave, and what risks they might pose in the future. Improved early warning systems and better sky survey technology will be essential for spotting these elusive visitors before they slip away. The fleeting glimpse we had of Threeey Atlas also highlights the extraordinary value of every single interstellar discovery. Observing the physical, chemical and orbital properties of an object that was born in another star system is a privilege that happens perhaps only once in a generation. By examining its dust, gas and structure, we are learning not only about this one comet, but also about the wider galaxy. What kinds of stars give birth to such wanderers? How do they change after travelling for millions or even billions of years through interstellar space? What secrets about alien chemistry are hidden in their dust? Studying the way dust behaves around Threeey Atlas gives scientists important clues about the true nature of comets that do not belong to our solar system. In our own neighbourhood of planets, comets are famous for their long and glowing dust tails. These tails appear when sunlight warms the comet's icy surface, causing its frozen gases to sublimate, turning directly from solid ice into gas. As this gas escapes, it drags tiny dust grains with it, creating a shimmering trail that can stretch for millions of kilometres across space. But Threeey Atlas did not behave like the lively comets we're used to. Instead of producing a grand sweeping tail, its dust activity was faint, uneven, and difficult to detect. This puzzled astronomers and made them wonder whether interstellar comets, the ones that wander between star systems, are fundamentally different from the ones born within our own solar system. When the interstellar comet Borisov passed through our system in the year 2019, it displayed a bright and obvious dust tail that was clearly visible even through medium-sized telescopes. In contrast, Threeey Atlas showed only a dim halo of dust, so faint that even the world's largest telescopes struggled to pick it out. This difference has sparked great interest, because it may mean that interstellar comets are far more diverse than we imagined. Normally, comets in the solar system carry large amounts of volatile ices such as water, carbon monoxide and methane. These substances evaporate easily when heated, which is why solar system comets often grow enormous bright comas and sweeping tails. Threeey Atlas, however, seemed different. Its weak and ghostly dust halo suggests that it may not contain as much of these easily sublimating materials. Instead, it could be made of more resistant compounds, rocky fragments, or carbon-rich organic material that do not evaporate as quickly and require much more heat to release gas. The faint halo still shows that Threeey Atlas was outgassing, but at a much weaker level than comets in our solar system. This hints that its surface has likely been hardened by countless ages of exposure to cosmic radiation, while drifting through the cold emptiness of the Milky Way. Over time, radiation can bake the outer layers of ice into a dark crust, which acts like armour and protects the deeper ices from escaping. As Threeey Atlas drew closer to the Sun, only the very outer surface warmed enough to release small amounts of gas and dust. This produced a thin haze, but not the grand streaming tail that Borisov proudly displayed. This small, hesitant outflow of dust also tells us something about the comet's possible origins. The presence of silicate grains, rocky minerals, in its faint coma suggests that Threeey Atlas may have come from a planetary system where both rock and ice were mixed together. Perhaps it was once part of a larger body, like a moon or a planetesimal, that was shattered and ejected into deep space. If that is true, then Threeey Atlas is not only a visitor from another star system, but also a fragment of a much larger and more complex world. The way its dust behaves reminds scientists that not all comets are created equal. Some, like those from the Oort cloud in our solar system, carry abundant ices that flare up when warmed. Others, like Threeey Atlas, may have travelled through interstellar space for so long that their surfaces have become crusted, their ices buried, and their activity muted. This raises an exciting possibility. Interstellar comets could hold secrets about the environments of their home star systems. Their chemistry, their surfaces, and even the faintness or brightness of their tails may reflect the cosmic histories they have endured. In the case of Threeey Atlas, its weak dust halo whispers of a long journey across the galaxy, endless exposure to radiation, and perhaps even an origin in a shattered planetary body. So, could Threeey Atlas be a remnant of a planetesimal, a small building block of planets that was broken apart in its home system and flung into the great interstellar void? Astronomers are still puzzling over the true nature of Threeey Atlas. Is it really just another comet, Or could it be something far more unusual, a broken-off fragment from a much larger world? One of the most fascinating possibilities is that Threeey Atlas might be a planetesimal fragment. Planetesimals are the original building blocks of planets. In young star systems, these small rocky and icy bodies form during the earliest stages of planet birth. Sometimes gravity pulls them together, helping them grow into moons and planets. Other times, violent collisions or the tug of giant planets tear them apart. If Threeey Atlas is indeed a shattered piece of a planetesimal, then what we're seeing is not just an ordinary comet, but a rare piece of another planetary system that was thrown into the dark between the stars countless ages ago, long before it wandered into our own solar system. We already know planetesimals are vital for understanding how planets and moons take shape. Around our Sun, many of them still remain today, quietly circling in places like the asteroid belt or the distant Kuiper belt. Yet, some do not stay put. When huge planets disturb their paths, or when catastrophic crashes occur, they can be ejected completely, set adrift into the galaxy. These wandering bodies travel for millions, or even billions, of years before crossing paths with other star systems. That is exactly how something like Threeey Atlas could have arrived here. Several clues hint that this object may indeed be a fragment of a larger body. First, its chemical makeup is unusual. While most comets are mostly made of frozen gases and dust, Threeey Atlas contains a mixture of ice and rocky minerals. Among them are silicate minerals, materials that usually form in the inner, warmer parts of planetary systems. This strongly suggests it may once have belonged to a larger, more complex body, perhaps a small moon or a differentiated planetesimal, where heat separated rock from ice. Such worlds are far more advanced than ordinary comets, which remain as untouched balls of primordial ice. Second, the shape and brightness changes of Threeey Atlas reveal that it is irregular, stretched or lumpy, instead of round. This fits the profile of an object that has been broken apart by a collision or by a violent gravitational encounter. When we see its light curve, how its brightness changes as it spins, it tells us it is no smooth sphere, but a jagged survivor of some ancient smash-up. Unlike many active comets, Threeey Atlas has only a faint coma, the glowing cloud of gas and dust that usually surrounds a comet near the Sun. Its weak activity suggests its outer layers have been scorched and weathered for ages by cosmic rays while drifting through interstellar space. These rays may have sealed off many of its deeper ice reserves, leaving it less explosive than a normal comet, but still preserving traces of its original materials. This endurance makes it appear tougher than fragile comets, hinting at its identity as a fragment rather than a delicate ice ball. If Threeey Atlas truly is a planetary fragment, then it was likely expelled from its home system during the chaotic early years of planetary formation. In young star systems, giant planets often wander inward and outward, pulling smaller bodies with them. Some are captured, while others are hurled into deep space. Sometimes the gravity of a passing star adds to the disruption, flinging fragments into interstellar journeys that can last millions upon millions of years. The path of Threeey Atlas across the heavens points toward the regions of Carina and Scorpius, star nurseries where countless young suns and planetesimals are being born. Perhaps it began its life in one of these crowded stellar cradles. As it passed through clouds of gas and dust, its orbit may have been nudged, shifting its speed and direction just enough to send it our way. Though its birthplace remains uncertain, its trail strongly suggests an origin not too far from an active star-forming region. To unlock more of its story, astronomers are studying how reflective its surface is and what chemicals are present. If its outer layers are rich in carbon-bearing compounds or organic materials, it could mean it once belonged to a carbon-rich planetesimal circling a larger planet at the edge of its star system. These carbon-heavy chemicals are common in the cold outer zones of solar systems, where ice, rock, and organic matter mix. If detected on Threeey Atlas, they would support the idea that we are looking at a tiny fragment of a much larger broken world, a survivor of an ancient planetary system that now drifts among the stars. Could it be an interstellar comet, or is it actually an asteroid from beyond the stars? When astronomers first spotted Threeey Atlas, they were faced with an urgent question. Was this mysterious traveller a comet, or was it more like an asteroid? At first, this might sound like a small detail, But in reality, the answer carries enormous importance. Deciding whether something is a comet or an asteroid changes the way scientists think about how worlds are built, how they change over time, and even how materials move through the universe. On the surface, comets and asteroids may look similar, but deep down, they are very different kinds of objects. Comets are often described as dirty snowballs. They are made of frozen ices mixed with dust and gases that can easily evaporate when warmed by a star. This evaporation creates the glowing halo of gas and dust known as the coma, as well as the long, beautiful tails that stretch across the sky. Asteroids, in contrast, are much drier. They are rocky or metallic worlds that usually stay silent and inactive unless something hits them or they crack apart. So where does Threeey Atlas fit? At first glance, it looked more like a comet. When it was discovered, astronomers noticed a faint glow around it, a thin dust halo, and some weak outgassing, a sign that frozen ices on its surface were turning into gas. But unlike well-known comets such as Comet Borisov, which blazed through space with a long and clearly visible tail, Threeey Atlas's activity was irregular and surprisingly faint. This caused some astronomers to doubt whether it truly deserved the title of a comet. Still, the story was not so simple. Spectroscopic studies, the close examination of the light it reflected, revealed the fingerprints of water ice and carbon monoxide, both of which are classic ingredients found in comets. This suggested that Threeey Atlas did have comet-like qualities, even if it was not acting like most comets we know. The weak outgassing seen around it could have been the result of small patches of ice on its surface warming up as sunlight hit it, slowly releasing gas and dust into space. But then came the puzzle. If Threeey Atlas truly was a comet, why did it not grow brighter and more active as it drew nearer to the Sun? One explanation is that it simply lacked large reserves of volatile ices. Another possibility is that its surface had been hardened by cosmic radiation and space weather during its unimaginably long journey between the stars. This protective crust could have sealed in its ices, stopping them from easily boiling away. Even stranger was its orbit. Most comets travel in elliptical orbits. These paths carry them close to the Sun, then sling them far back into the outer reaches of the solar system, sometimes repeating the cycle for millions of years. Threeey Atlas, however, followed a very different course, a hyperbolic orbit. This means it is not bound to the Sun's gravity at all. Instead, it is on a one-way journey, cutting through our solar system before disappearing forever into the depths of interstellar space. This was another clue that Threeey Atlas was not a typical comet. Comets usually come from icy reservoirs like the Kuiper Belt, which lies beyond Neptune, or the vast, distant Oort cloud, which may surround the solar system like a shell. Asteroids, by contrast, are usually found in stable belts, the asteroid belt between Mars and Jupiter, or occasionally in the Kuiper Belt as well. But Threeey Atlas belonged to neither group. It was not a permanent resident of our solar system at all. It was an interstellar wanderer, a drifter between the stars. And then there was the question of its surface. Asteroids are mostly rocky, with silicates and metals dominating their composition. Some even contain a small sprinkling of carbon-rich material, but they are generally dry. Comets, on the other hand, are icy bodies, with fragile mixtures of frozen water, carbon compounds, dust, and organic materials that often burn away when they near the Sun. Threeey Atlas seemed to show a little of both. It carried water ice and carbon monoxide, like a comet, but also had mineral dust more typical of an asteroid. All of this left astronomers with a tantalizing conclusion. Threeey Atlas may not fit neatly into either category. Instead, it could be a hybrid, a cosmic in-between, part comet, part asteroid. This possibility makes it even more fascinating. Perhaps Threeey Atlas began its life as a comet in another star system, only to be reshaped by billions of years of radiation and interstellar travel, leaving it with the mixed identity we see today. Its strange nature continues to spark debate, reminding us how much we still have to learn about the travellers that drift between the stars. How was Threeey Atlas able to withstand the harsh radiation and dangers of interstellar travel? People all over the world are deeply curious about the long and lonely voyage of Threeey Atlas, its journey from its unknown home system far away among the stars to its brief and fleeting visit with our solar system. They want to know everything. what it is made of, how it travelled across the galaxy, and most importantly, how it managed to survive the deadly emptiness of interstellar space. That space between the stars is one of the harshest environments imaginable. It is filled with radiation, blasted with cosmic rays, and chilled to temperatures so low that they are hundreds of degrees below freezing. To make matters worse, the space between stars is almost completely empty. In such a place, most fragile objects would quickly fall apart, their surfaces stripped and destroyed by the endless storm of high-energy particles. Yet somehow, Threeey Atlas endured. Against all odds, it passed through the galaxy's cold and destructive void and entered our solar system still mostly intact. To understand how this mysterious traveller made it through such a dangerous and unimaginably long journey, scientists rely on what are called thermal models. These are powerful computer simulations that try to predict how an object like Threeey Atlas reacts to heat, radiation, and space weather as it drifts for millions or even billions of years between the stars. One of the greatest threats to such objects is cosmic radiation. As Threeey Atlas sailed through interstellar space, it would have been constantly bombarded by invisible bullets, high-energy particles arriving from every direction at nearly the speed of the light. These cosmic rays are mostly made of charged particles, protons, electrons, and even the nuclei of atoms. Though tiny, when they strike a surface again and again over vast stretches of time, they can alter its chemistry, erode it, and leave behind lasting scars. For Threeey Atlas, this bombardment likely darkened and hardened its surface. The constant particle strikes could have melted ices and reshaped simple molecules into more complex organic compounds. Over countless years, this would have created a dark radiation-treated crust, a toughened outer shell that scientists believe now coats the object. Ironically, this very damage may have been its shield. By forming a hardened layer on the outside, the crust could have protected the fragile ices and other volatile materials trapped beneath, keeping them from being destroyed too early by the environment of space. The survival of Threeey Atlas depended heavily on its ability to maintain thermal balance during its endless drift through interstellar space. Out there, far from any star, the temperatures plunged to extremes, hundreds of degrees colder than the coldest places on Earth. In such conditions, water ice, frozen carbon monoxide, and other volatile substances stay locked in their solid state. This deep freeze acted like a natural freezer, preserving the original ingredients of the object for untold ages. But when such an interstellar wanderer finally approaches a star, everything changes. The warmth from the star begins to thaw the surface, and those frozen volatile compounds start to sublimate, transforming directly from solid to gas. In the case of Threeey Atlas, the sunlight it received near our sun was enough to trigger a little sublimation. That is why it displayed a faint ghost-like coma and a delicate dust trail as it passed through the inner solar system. Thermal models also predict that objects like Threeey Atlas suffer from what is called thermal shock when they make this transition. Imagine an object that has been frozen for millions or billions of years in deep space suddenly being exposed to the heat of a star. Its surface would warm dramatically in a short time, cracking and fracturing under the stress. For Threeey Atlas, this sudden heating may explain why it showed only weak activity, just a thin release of gas and dust. Its thick crust likely acted as insulation, keeping most of the ices hidden below intact, while allowing only small amounts to escape into space. Another factor that scientists consider is how evenly an object heats up. Because Threeey Atlas is small and oddly shaped, it would not warm evenly like a larger round comet. Some patches of its surface would have absorbed more sunlight than others, leading to uneven heating. This could cause bursts of outgassing in specific spots, rather than producing the dramatic and balanced tail of a typical comet. This uneven activity may explain why Threeey Atlas appeared so faint and subdued compared to comets like Comet Borisov, which showed off a more familiar and striking tail during its passage. However, cosmic rays also shaped the thermal history of this wandering visitor. Over spans of millions or billions of years, these high-energy particles work like invisible sculptors, slowly wearing down its outer layers and building the dark, radiation-processed crust we see today. Beneath that protective shell, however, the more volatile and fragile materials remained safely preserved, like secrets hidden inside a locked vault, waiting until Threeey Atlas finally crossed paths with our sun and revealed a little of its story. In the strange and fascinating case of Threeey Atlas, scientists believe that its outer layer, rich in organic material, may have acted like a protective shield. This dark crust covered and guarded the fragile volatile ices buried deep inside. Without such a protective layer, the ices would have evaporated quickly as the object drifted through the vast emptiness of interstellar space, bombarded constantly by radiation and cosmic rays. Instead, the shield slowed down this process, allowing Threeey Atlas to endure its long, lonely voyage between the stars. An especially intriguing mystery lies in what happened to its organic matter during this interstellar journey. Cosmic radiation has the power to change molecules, sometimes even creating new and more complex ones. On the surfaces of comets and planetesimals, for example, radiation can form carbon dioxide and other intricate chemicals. The fact that molecules like these may exist on Threeey Atlas gives weight to a very bold idea: that objects wandering between stars could act as carriers of prebiotic chemistry, scattering the seeds of life across the galaxy. Perhaps Threeey Atlas collected extra organics, similar to those on comets, during its travels. If so, it may have been one of nature's couriers, quietly transporting the building blocks of life far beyond its birthplace. But there is still much we do not know. Did these delicate organic compounds truly survive the harsh temperatures of deep space? Or did they break down over time? Some scientists suggest that the icy shell of Threeey Atlas could have served as a kind of freezer, keeping them safe, while others remain cautious. The object's path through our solar system also tells a fascinating story. Unlike ordinary comets, which orbit the Sun again and again, Threeey Atlas followed a hyperbolic orbit, meaning it was simply passing through at incredible speed. Because of this, its encounter with the Sun was extremely brief. It never lingered long enough to be heated dramatically or to erupt with activity like comets usually do. Instead, it gave off only faint streams of gas and dust, a quiet traveller rushing onward, untouched by the kind of transformations we normally witness in icy visitors from the outer solar system. Another great mystery is whether Threeey Atlas had passed through other star systems before it reached us. Since it came from the depths of interstellar space, it is very unlikely that its journey was a straight shot from one point to our solar system. Instead, it must have wandered through the Milky Way for millions or even billions of years, drifting across stellar neighbourhoods, weaving past young stars, perhaps even being tugged this way and that by invisible gravitational hands. Astronomers know that interstellar objects are often born when planets migrate in young solar systems. The shifting of giant planets can fling comets and planetesimals outward, hurling them into the galaxy to roam freely. Once ejected, they follow paths that no star can hold, hyperbolic orbits that carry them from system to system. Threeey Atlas is one of these cosmic wanderers, and its path confirms it will never return. It was a visitor, not a resident. When scientists trace its orbit backward, they find that it points toward a region of space near the constellations Carina and Scorpius. These stellar nurseries are crowded with newborn stars and heavy activity. It is tempting to imagine that Threeey Atlas may once have drifted among them, perhaps even being nudged onto its course by the gravity of a massive young star. Yet the galaxy is vast, and while simulations can suggest possibilities, it is nearly impossible to say for certain which stars it might have passed. Still, its long journey cannot have been uneventful. Interstellar space is not truly empty. It is filled with molecular clouds, cosmic dust, high-energy radiation, and the debris of ancient supernovae. As Threeey Atlas moved through this wilderness, each encounter must have left faint scars. Its surface likely carries the marks of cosmic weathering, chemical changes, dust impacts, radiation burns. These cosmic fingerprints may one day help us retrace its path, revealing whether it once brushed past another star system. Even if the chance of a direct passage through a star system is relatively low, models show that many interstellar objects do, in fact, wander across multiple stellar regions over vast timescales. So while Threeey Atlas may not have approached stars closely, it almost certainly passed through star-forming clouds and dense stellar environments that quietly reshaped its surface. Today, what makes Threeey Atlas so valuable to scientists is that its outer skin still holds clues to this long history. Its faint activity and thin halo of dust hint at a mixture of ices and organics, altered over uncounted ages. By studying these changes, researchers may discover not only how it survived its journey, but also whether it once carried whispers of other worlds on its surface. Tiny traces of chemistry born in distant stellar nurseries. And that is why Threeey Atlas matters even for planetary defense. Every interstellar visitor gives us more knowledge about the kinds of objects drifting through the galaxy. By studying them, we learn how to recognize them, track their paths, and understand their nature. One day, such knowledge may help us prepare should a less harmless visitor come hurtling our way. 3. Atlas is like a mysterious traveller from beyond the stars, a rare visitor that briefly passed through our solar system before continuing on its endless journey. Its short visit was more than just a curious astronomical event. It carried valuable lessons for how we might protect our planet in the future. Even though Threeey Atlas itself never posed a direct danger to Earth, its sudden arrival reminded us of potential problems that could arise as we continue to discover more wandering objects, not only in our own solar system, but also from the vast spaces between the stars. By studying Threeey Atlas, its unusual speed, its strange elongated shape, its faint level of activity, and its swift path through space, scientists realized they could improve early warning systems, create better ways to recognize cosmic threats, and develop new strategies for handling them if one ever headed toward Earth. Up until now, most planetary defense efforts have focused on near-Earth objects, often shortened to NEOs. These include comets and asteroids that circle within our solar system and sometimes pass close enough to Earth to raise concerns. Over the last few decades, astronomers have gotten much better at spotting these objects and predicting their paths. But interstellar visitors like Threeey Atlas bring an entirely new challenge. Unlike NEOs, they come from outside our solar system, travelling at far higher speeds, and they leave us with far less time to prepare if they happen to be on a dangerous course. Speed is one of the greatest challenges. Most ordinary comets and asteroids move at about 20 to 30 kilometers per second, but interstellar objects can be much faster. Threeey Atlas was racing toward the Sun at nearly 60 kilometers per second, about twice the speed of the average solar system comet. Because of this, it was far more difficult to spot early, and once it appeared, astronomers had only a short window to study its path and judge whether it might pose a threat. Its hyperbolic orbit showed that it was simply passing through, on a one-way journey never to return. This meant it was not dangerous to Earth, but it also served as a warning. If another fast-moving object like this were ever heading directly at our planet, we would have very little time to act. An interstellar body on a collision course could strike with almost no warning, leaving humanity with only limited chances to respond, whether by trying to deflect it or, in the worst case, evacuating threatened regions. Another difficulty is that such objects are very hard to see. Based on what we learned from Threeey Atlas, many interstellar wanderers are small, dim, and quiet, giving off little gas or dust. They often blend into the background of stars, making them nearly invisible with today's technology. Some may already be passing silently through our solar system without us even knowing, especially if their paths do not bring them close to Earth or the regions of the sky we regularly survey. Large sky-watching projects like Atlas and Pan-STARRS have improved our ability to spot near-Earth asteroids, but they are not designed for finding faint, fast-moving interstellar travellers. In fact, Threeey Atlas was not detected until after it had already passed its closest point to the Sun. This late discovery highlights the urgent need for more sensitive telescopes and new methods of searching the skies, so we can catch these cosmic guests sooner. Planetary defense plans also need to evolve. Current methods, such as using a spacecraft to crash into a threatening asteroid to nudge it off course, called the kinetic impactor method, or even considering nuclear devices for deflection, were designed with slower, solar system-based objects in mind. Interstellar visitors, however, move so quickly that these strategies may not work. New types of spacecraft, new propulsion systems, or entirely new approaches may be needed if we're to defend Earth against such high-speed threats. Studying the size, structure, and material strength of objects like Threeey Atlas helps scientists refine these defense plans. Each detail we uncover tells us more about what kinds of objects we might face and how to deal with them. These studies also improve our understanding of space weather, the flow of cosmic dust, icy grains, and even organic molecules that sometimes travel with these objects. Some of this material might even include fragments of distant planets, carrying chemical clues about how matter behaves in other star systems. Such discoveries could help us understand not only planetary defense, but also the origins of life itself in the wider galaxy. The discovery of Threeey Atlas is like opening a brand new doorway into space exploration. For the very first time, astronomers began to think seriously about sending a spacecraft to chase down and study visitors from other star systems as they pass through our own. Even though Threeey Atlas's brief journey across the solar system was too short for us to send a mission directly, its passing makes us dream about the future, about the possibility of one day capturing such objects, or at least sending a robotic probe to fly alongside them and reveal their secrets. The idea of sending a spacecraft to a traveller from another star system is thrilling, but it is also one of the hardest challenges space exploration has ever faced. To succeed, humanity would need cutting-edge technology, entirely new methods of propulsion, and careful planning to catch something racing through space at incredible speeds. One of the clearest obstacles is speed. When Threeey Atlas crossed our skies, it was moving at about 60 kilometers every second. That is far faster than anything humans have ever built. By comparison, most spacecraft designed to move around our solar system travel at only about 10 to 20 kilometers per second. This means that if we ever want to intercept an interstellar object like Threeey Atlas, our spacecraft must be fitted with engines that can at least match, if not exceed, those breathtaking velocities. To catch such a runaway traveller, the spacecraft would first need to adjust its path within the solar system to line up with the object's trajectory. That often means relying on gravity assists, slingshot manoeuvres that use the pull of giant planets such as Jupiter or Saturn to fling the spacecraft forward at higher speeds. Gravity assists have already been used successfully in missions like Voyager, Galileo and Cassini, and they remain one of the best tools for gaining speed without carrying huge amounts of fuel. Yet even these powerful boosts have limits. When faced with an object as fast as Threeey Atlas, even the mightiest slingshot may not be enough. Consider NASA's Parker Solar Probe, one of the fastest spacecraft ever built. It was designed to study the Sun up close and can reach record speeds of around 700,000 kilometers per hour. That number sounds astonishing, but even this champion of speed would still be too slow to catch up with an interstellar wanderer like Threeey Atlas. Clearly, we will need something more advanced than anything we have today. One promising idea is the solar sail. A solar sail is like an enormous, ultra-thin mirror that captures the gentle push of light itself. Every photon from the Sun carries momentum, and when it strikes the sail, it gives the spacecraft a tiny nudge forward. Over time, these nudges add up, and the spacecraft can build speed without burning any fuel at all. With a solar sail, a ship could keep accelerating for months or even years, eventually reaching the kind of speeds needed to catch an object racing between the stars. This concept is not just science fiction. Projects such as Breakthrough Starshot already imagine sending fleets of tiny, lightweight probes pushed by powerful laser beams. These miniature spacecraft could potentially reach 20% of the speed of light, fast enough to reach nearby star systems within a single human lifetime. A scaled version of this idea could one day be adapted to chase down interstellar objects as they flash through our solar neighbourhood. Another advanced option is ion propulsion. Unlike traditional rockets that burn chemical fuel, ion engines use electricity to charge atoms of xenon gas and shoot them out at incredible speeds. Ion drives produce only a small amount of thrust at any given moment, but they can operate for years without stopping. This means a spacecraft can slowly but steadily build up speed over time. NASA's Dawn mission, which visited the asteroid Vesta and the dwarf planet Ceres, proved just how powerful this technology can be. If improved further, ion propulsion might allow us to design a probe that could eventually catch up to an interstellar wanderer, though it could take many years. But no matter how powerful the engines are, timing is everything. Threeey Atlas was moving so quickly that by the time astronomers spotted it, it had already passed the point where a mission could have been launched. This was an important lesson. To have any hope of chasing these visitors, we need to detect them much earlier. Thankfully, new sky surveys such as the upcoming Vera Rubin Observatory will give us sharper eyes and quicker warnings. With the earlier detection, we could prepare a spacecraft and launch it in time to intercept the next interstellar visitor. There is another challenge: the length of such missions. Objects like Threeey Atlas spend only a few months in the inner solar system before vanishing back into the dark. But to chase them, a spacecraft would need to operate for many years, possibly decades. Along the way, it would have to survive cosmic radiation, collisions with tiny micrometeoroids, and the freezing cold of deep space. That means we would need stronger materials, smarter onboard systems, and new designs that can last far longer than most spacecraft today. If we manage all this, what might we learn? The path or trajectory of interstellar objects holds deep clues about the larger motions of stars, gas, and dust in our galaxy. Every visitor like Threeey Atlas is a messenger, carrying with it a story about the birthplaces of stars, the scattering of planetary fragments, and the hidden rhythms of the Milky Way itself. So, when the next cosmic traveller rushes past, will humanity be ready to follow? Threeey Atlas's short visit to our solar system is not just about learning what this mysterious traveller is made of, it is also a rare window into how our galaxy itself works. By carefully watching its movement, astronomers can unlock secrets about how interstellar objects travel, how the Milky Way's gravitational field shapes their paths, and even how stars and galaxies influence one another on their long journeys through space. Most objects in our solar system, such as planets, asteroids, and comets, follow closed circular or oval paths around the Sun because of the Sun's gravity. Threeey Atlas, however, is different. It is not bound to the Sun at all. Instead, it follows what is called a parabolic path, a kind of one-way ticket through our neighbourhood in space. The Sun's pull cannot keep it, and so once it finishes passing through, it will continue outward and never return. That makes every observation of it priceless, because once it is gone forever. By measuring its speed and mapping its orbit, astronomers can test important ideas about how stars move, how galaxies interact, and how cosmic forces govern the endless traffic between the stars. One of the first big lessons Threeey Atlas gives us is how the movement of stars can change the course of wandering interstellar objects. Its path suggests it may have come from a faraway region, near the constellations of Carina and Scorpius, areas rich with young stars that are still forming. Perhaps Threeey Atlas was once part of a young planetary system there, until gravitational tugs from nearby stars flung it out into deep space, like a stone skipping across a pond. When scientists trace its path backward in time, they see how encounters with massive stars or giant clouds of gas and dust could have bent its orbit, sending it on this fast, unpredictable voyage. This helps them understand how interstellar objects are scattered all across the Milky Way, and why some end up passing near Earth. Its very high speed hints that it may have come from the outer parts of the galaxy, where stars are fewer and more spread apart. By comparing its motion to computer simulations of how stars drift and migrate, astronomers can test and improve their models of how the Milky Way has evolved over billions of years. If future telescopes discover more visitors like Threeey Atlas, scientists will be able to build an even clearer picture. They will see how these objects are thrown out of their home systems, how they are shaped by the gravity of nearby stars and molecular clouds, and how they eventually become lonely travellers across the galaxy. Threeey Atlas also reminds us that the Milky Way is not a fixed, still place. It is a living, moving system. Stars orbit the galactic centre, clouds of gas flow and collide, and even the invisible dark matter plays its part. Every tug of gravity between stars or planets can tip the balance of a system, sometimes ejecting whole worlds or comet-like bodies into the great interstellar sea. Threeey Atlas may itself be a product of such ancient chaos, perhaps nudged by the passage of a nearby star or by shifting clouds of dust and gas that reshaped its fate. Studying objects like this also takes us deeper into the story of how our galaxy formed and changed over time. Most worlds, planets, moons, asteroids and comets are bound to stars. But the fact that objects can be thrown out into the emptiness tells us that the Milky Way has always been restless. Long ago, when stars were still being born and young planetary systems were unstable, countless bodies may have been cast out into space. Threeey Atlas is living proof of that history, like a fossil drifting between the stars. As astronomers tracked its speed and direction through our solar system, they also measured how it interacted with the Sun's gravity. Its rapid passage showed that it came from a part of the galaxy where gravity is weak, far from the reach of big star clusters or powerful stellar systems. That makes it especially valuable for testing how galactic gravitational fields influence wandering objects. Each observation helps refine models of how stars move and how the Milky Way itself flows through the universe. On an even larger scale, Threeey Atlas helps us learn about the invisible matter that fills the spaces between stars. As it glided through our solar system, scientists watched closely to see how it responded to cosmic radiation, interstellar gas, and the solar wind. These tiny effects can reveal how dense the material between the stars is, letting us build a kind of map of the Milky Way's hidden structure of gas and dust. Step by step, visitors like Threeey Atlas allow us to uncover the conditions of the galactic medium, the vast ocean in which all stars float. Did Threeey Atlas leave anything behind? One of the most fascinating mysteries about Threeey Atlas is whether it left behind any cosmic junk as it rushed through our solar system. Threeey Atlas is not from our neighbourhood at all. It is an interstellar traveller, a wandering object that entered our solar system from a distant star system far beyond our own sun. While it may have stayed mostly in one piece during its brief visit, its incredible speed could have shaken loose tiny bits of matter, micrometeorites and dust grains, that fell away from its surface. Some of these minuscule fragments may have drifted into the endless void of our solar system, while others might have plunged into Earth's atmosphere, burning up as faint streaks of light too small for the human eye to notice. If so, those pieces have now become part of the vast cloud of cosmic dust that surrounds our solar system and stretches far beyond it. Studying how interstellar guests like Threeey Atlas interact with the environments they pass through is one of the most exciting challenges for astronomers. As Threeey Atlas moved closer to the Sun, it faced stronger and stronger blasts of solar energy. This heating likely caused some of its outer layer to weaken and peel away. Ice is buried in its crust. Ice is made of water, carbon dioxide, or perhaps even stranger frozen chemicals, would have vaporized, turning directly into gas. Along with them, dust and tiny rocky grains would have been freed into space, creating a faint tail or trail behind it. These micrometeorites, no bigger than grains of sand, are the cosmic crumbs left behind by interstellar wanderers. But Threeey Atlas's journey was not easy. Racing through space at such high speed meant it was constantly bombarded by harsh conditions, intense solar radiation, scorching heat near the sun, and the invisible but powerful strike of cosmic rays. All of these forces slowly chipped away at its surface, stripping off material and scattering it into space. Even if only a small amount of dust was lost, those particles could have joined the interstellar cloud of dust that constantly drifts through our solar system. Although these fragments are far too tiny for us to see without powerful instruments, they are incredibly important. Space missions from NASA and other agencies have shown that cosmic dust is not just leftover junk. It plays a key role in building planets, moons, and other celestial worlds. Even the microscopic dust particles that fall into Earth's atmosphere tell us stories about their parent bodies, carrying with them chemical signatures that may reveal where they came from and what they are made of. If Threeey Atlas really did shed a dust trail, it might even have added, in a very small way, to the streams of particles that cause Earth's meteor showers. Each year in the month of August, for example, our planet passes through the debris left behind by Comet Swift-Tuttle, creating the famous Perseid meteor shower. If Threeey Atlas had left a similar path of dust and rock, Earth could, in theory, one day cross it. However, because Threeey Atlas passed through so quickly, it is unlikely that it left behind enough material to noticeably affect any of our yearly meteor showers. Still, comparing Threeey Atlas to other interstellar visitors gives us some clues. Comets like Borisov, for instance, have been observed releasing large amounts of dust and gas as they move through the inner solar system. Since Threeey Atlas was also likely made of ice, it probably released at least some dust, though less than our familiar comets. That means its contribution to the interstellar dust cloud in our solar system was probably small but not non-existent. Even a small contribution, however, is meaningful. Every grain of dust left behind by interstellar objects gives scientists a precious sample of material from faraway star systems. By studying these traces, astronomers hope to uncover secrets about how planets form in other systems and about the chemistry of the space between stars, the interstellar medium. Some dust particles may even carry organic molecules, the raw ingredients that can one day lead to life. This is why the path of Threeey Atlas is so important. Each interstellar object we discover is a clue to a much larger puzzle. How many of these cosmic wanderers are out there? How often they pass through our solar system, and what they can teach us about the galaxy beyond our sun. Threeey Atlas may have come and gone in a short time, but the mysteries it left behind could help us understand not just a single strange visitor, but the entire hidden population of interstellar travellers roaming the Milky Way. 3. Atlas's brief but fascinating journey through our solar system has raised big and exciting questions about what kinds of interstellar travellers might be drifting through our galaxy. Threeey Atlas is only the second confirmed object from beyond the stars ever seen passing through our solar neighbourhood, following the first discovery of the mysterious Oumuamua in the year 2017. Together, these two visitors have given us rare and precious glimpses into a part of the universe that has remained largely hidden: how objects move between the stars. By studying the path of Threeey Atlas, scientists are beginning to piece together clues about how often such visitors appear, where they might come from, and how they behave when they briefly sweep past our sun. The very fact that astronomers were able to detect Threeey Atlas at all is remarkable, considering how quickly it shot through the solar system. Its discovery, added to that of Oumuamua, suggests that interstellar objects may not be as uncommon as once imagined. In fact, they might be far more plentiful. Only many pass through unnoticed because of their great speed and short time within reach of our telescopes. Threeey Atlas was visible for only a few months before it slipped back into the darkness of interstellar space. This fleeting appearance reminds us that there could be countless other wanderers rushing through the solar system right now, invisible to us. Thankfully, sky surveys such as the Atlas program and Pan-STARRS are getting better at spotting these quick-moving visitors, but the true number of interstellar objects drifting across the Milky Way remains a great mystery. It may be that Threeey Atlas was only the tip of the cosmic iceberg, a hint of a much larger population of hidden travellers. If this is true, then interstellar objects could be quite common. Many of them may be fragments of planets, icy comets, or rocky asteroids that were once part of their original star systems. Over billions of years, gravitational encounters with giant planets, or even with the stars themselves, may have flung these bodies out into the galactic wilderness. Once adrift, they can wander endlessly between the stars until, by chance, they fall into the pull of another system, just as Threeey Atlas did when it brushed past our sun. Discoveries like this one, especially when combined with future detections, will allow astronomers to begin estimating just how many of these objects roam the galaxy. They will also help us understand how often such visitors pass through our own solar system. But the importance goes even further. By tracking how interstellar objects move and how their paths are twisted by the sun and planets, scientists can refine their knowledge of how gravity works on the grand stage of the Milky Way. The unusual speed of Threeey Atlas tells us something important. It was moving far faster than most ordinary comets and asteroids in the solar system. This suggests that it likely came from regions of the galaxy where gravity is weaker, far from the tightly bound zones near stars and planets. This supports the idea that many such objects are born at the edges of star systems, hurled into interstellar space after close encounters with massive planets or near collisions with stars. Even more, the exact trajectory of Threeey Atlas is teaching astronomers about how such objects interact with our solar system. Visitors moving at such extraordinary speeds are harder to study than local comets, because they rush past the sun too quickly for long-term observation. Yet, every time astronomers manage to track one, they gain new data about how these bodies behave, how their paths are bent by gravity, and how they might interact with planets or smaller objects along the way. Could one of these interstellar visitors ever be captured? Could the sun's pull, or perhaps the combined forces of the planets, snare a traveller like Threeey Atlas and keep it here, turning a fleeting guest into a permanent member of our solar family? Bringing an object like Threeey Atlas, a wanderer from the vast spaces between the stars, into our own solar system might sound like the plot of a science fiction story. Yet astronomers have seriously asked the question, could such a thing really happen? The challenge lies in the incredible speed of these interstellar visitors. Threeey Atlas, for example, was racing through space at nearly 60 kilometers every second. That is far faster than the Sun or the planets can usually handle. The gravitational pull of our solar system simply does not have enough strength to grab hold of something moving that quickly. Instead, most of these visitors follow what scientists call hyperbolic paths, routes that carry them in, let them swing past the Sun, and then send them away forever, never to return. But is it at least possible, even in theory, to capture an object like Threeey Atlas and place it into orbit around the Sun, the Earth, or one of the giant planets? The answer is yes in theory, but with an almost impossible level of difficulty. To understand why, we must look closely at speed and energy. Asteroids and comets that live in our solar system move in elliptical orbits, where the Sun's gravity keeps them bound. Interstellar objects, however, come from far away and tear through space at much higher speeds. They are not tied down by the Sun's pull, and unless something slows them, they will simply keep going. To trap one of them in orbit, it would need to lose a great deal of its kinetic energy, the energy of its motion. This process is called gravitational capture, and it is extremely rare. The most famous case we know is Comet Borisov, discovered in the year 2019. It was the very first interstellar comet ever detected. Yet even Borisov was never fully captured. Its orbit was also hyperbolic, which meant it too came and went without ever becoming bound to the Sun. So how could such a capture ever happen? The best chance would be if a massive planet, something like Jupiter or Saturn, used its enormous gravity to tug at the speeding object. If the interstellar visitor passed at just the right angle and speed, the planet's pull could slow it down enough to make it loop briefly around the planet or even fall into orbit around the Sun. But everything would have to line up with astonishing precision. The odds of this happening naturally are extremely low, because the universe rarely sets up such perfect coincidences. Even the mighty gravity of the gas giants usually cannot slow down an object that is already moving so fast. In most cases, the visitor simply rushes past, still travelling too quickly to be caught. To make capture more likely, astronomers have imagined complicated strategies, such as using multiple gravitational assists, a method spacecraft already use to change speed by flying close to planets. In theory, if an interstellar object happened to pass by several planets in just the right sequence, each pass could slow it down little by little until it finally entered a stable orbit. But in practice, such a dance would take enormous amounts of time, perfect timing, and perhaps even the help of human technology. The only other way an object like Threeey Atlas might slow down enough is if it had already been slowed during its long journey through space. For example, if it had close encounters with other stars or planets in its travels, its speed might drop before reaching our solar system. But even then, the odds are tiny. And yet, even without capture, Threeey Atlas gives us something priceless. It is more than just a wandering rock. It is a time capsule from another star system. Inside it are materials that formed around a distant star in a region of the galaxy far from our own. It carries with it frozen samples of the building blocks of planets, preserved across unimaginable stretches of time. Studying it is like reading a cosmic letter written by another world. Interstellar objects like Threeey Atlas are usually the broken pieces of larger worlds, shattered moons, fragments of planets, or small building blocks known as planetesimals. These fragments were thrown out of their home systems long ago by the tug of giant planets or the disturbances of nearby stars. Because they have never been exposed to the heat and chemistry of our solar system, they carry a kind of untouched purity. When astronomers observed Threeey Atlas as it passed by, they found signs of water ice, carbon monoxide, and other fragile chemicals on its surface. These are substances commonly found in the cold outer zones of star systems. That clue suggests that Threeey Atlas may have been born in a faraway frozen region, much like where our own comets originate. So while capturing such an object into orbit may remain close to impossible, the visit of Threeey Atlas still offers us an extraordinary gift, a fleeting glimpse into the hidden chemistry and history of a star system beyond our own. When astronomers first spotted the strange traveller known as Threeey Atlas, they quickly realised that it was more than just another icy body drifting through the dark. This object was not simply a frozen ball of dust and rock, it was something far more precious, a cosmic messenger carrying with it secrets from a place and a time so far away that no human imagination could easily grasp it. What makes Threeey Atlas so extraordinary is not only its chemical makeup, though that alone would already be fascinating. It is the story that its atoms, ices and rocks might tell us. In many ways, an object like this is a kind of time capsule, one that was sealed billions of years ago in a star system far beyond our own. Long before our sun was born, before Earth had oceans, mountains or even a sky, a molecular cloud drifted quietly somewhere else in the Milky Way galaxy. That cloud was vast, cold, and full of raw ingredients: hydrogen, carbon, oxygen, silicates, and icy molecules that would eventually come together to form new stars and planets. Within that cloud, conditions such as temperature, density, and chemical balance played a key role in shaping whatever emerged. Threeey Atlas was born in that kind of environment. Billions of years ago, pieces of dust and gas stuck together inside the parent cloud, slowly shaping themselves into a solid body. Then, through the complicated dance of gravity, collisions, and cosmic forces, this small body was cast out of its home system, becoming a lonely traveller in the endless darkness of interstellar space. Unlike the asteroids, comets, and moons in our solar system, which have been constantly heated, bombarded, and changed by the sun's energy and by collisions with one another, Threeey Atlas has spent most of its long existence untouched. For billions of years, it has floated in the silent cold between the stars, shielded from the kind of constant wear and tear that alters most space rocks in our solar neighbourhood. That is what makes it priceless. In its icy and rocky shell, Threeey Atlas may still carry the original fingerprints of its birth cloud. By studying it, astronomers could peer into a chapter of cosmic history that is far older than anything we can study here at home. Imagine being able to scoop up a sample of water or dust that had been preserved since the dawn of another planetary system. That is what Threeey Atlas offers scientists, a direct clue about what conditions were like in a system that might have been completely unlike our own. By examining its surface and interior, researchers can begin to piece together the chemical processes that shaped it. If molecules like amino acids, the simple organic compounds that form the foundation of proteins, are present, it would mean that the environment where Threeey Atlas was formed was friendly to life. These tiny molecules are the stepping stones that eventually build living cells, and if they exist inside an interstellar visitor, it would strongly suggest that the universe is fertile with life's ingredients. Some comets in our own solar system carry these kinds of molecules, but finding them in an interstellar object like Threeey Atlas would carry an even deeper meaning. It would suggest that the recipe for life is universal, repeated in many corners of the galaxy, and not unique to our sun's planets. Threeey Atlas could then be thought of as a cosmic courier, delivering packages of life's raw ingredients across unimaginable distances. As it drifts from one star system to another, it might quietly spread the seeds of life, leaving behind the chemical foundation upon which new biological worlds could grow. But Threeey Atlas might be more than just a carrier of molecules. Its rocky materials, such as silicates and metals, hint that it may once have been part of a much larger body, perhaps a moon, a planetesimal, or even a fragment broken off during the violent youth of its parent system. If this is true, then Threeey Atlas is not only a messenger, but a fossil from a shattered world. Just as fossils on Earth give paleontologists clues about animals and plants that lived long ago, Threeey Atlas gives planetary scientists a glimpse into the geology of another solar system. Its dust, minerals and ices could reveal what kinds of planets were forming around its star billions of years ago, and whether those planets were rocky like Earth, icy like Europa, or something altogether different. This idea excites astronomers because it expands their vision of what kinds of worlds may exist in the galaxy. By studying one tiny rock that wandered into our neighbourhood, we may learn about entire systems of planets that otherwise remain invisible to us. For planetary scientists, objects like Threeey Atlas are nothing less than a goldmine. Here is a chance to study material that does not belong to the solar system, material that formed under conditions we cannot fully recreate or even observe elsewhere. Every grain of dust, every trace of ice on its surface is a clue in a larger puzzle. Together, these pieces could help astronomers build better models of how stars and planets form, evolve, and possibly even host life. By comparing the makeup of Threeey Atlas to the asteroids and comets we already know, scientists can spot similarities and differences. For example, Does it have more carbon than local comets? Does it carry exotic ices we do not normally find near the Sun? Are its silicates arranged in crystals or in glass-like structures? Each answer helps refine our understanding of not only Threeey Atlas itself, but of the entire process of planet building across the galaxy. Perhaps the most thrilling aspect of Threeey Atlas is how it connects to the mystery of life's beginnings. For decades, scientists have wondered whether life began only once, in our oceans about 4 billion years ago, or whether the ingredients of life are sprinkled everywhere in the cosmos, ready to blossom whenever conditions are right. Interstellar objects like Threeey Atlas breathe new energy into these debates. They suggest that life's building blocks might not be limited to one small corner of the Milky Way. Instead, they could be scattered across the galaxy, carried by wandering icy bodies that drift for billions of years before crashing into young planets. This idea is captured in the Panspermia hypothesis, which proposes that life's essential molecules, or even microscopic life itself, could travel from star to star, seeding new worlds. If Threeey Atlas holds amino acids, nucleobases, or other carbon-rich compounds, it would provide powerful evidence in support of this idea. In that case, Earth might not have been unique at all. Instead, our world could simply be one of many planets that were fertilized by the wandering couriers of life. The thought is staggering. Perhaps billions of years ago, long before humans, dinosaurs, or even trees, some interstellar body like Threeey Atlas struck the young Earth. As it burned in the atmosphere or dissolved in ancient oceans, it might have delivered the very molecules that would later build DNA and proteins. Without that chance collision, perhaps Earth would still be barren rock and water, and if it could happen here, why not elsewhere? How many other planets circling distant suns have been visited by such objects? How many oceans might have quietly begun brewing life because of a gift carried by a wandering interstellar traveller? The discovery of Threeey Atlas is only the beginning. Before this, humanity had identified only one other confirmed interstellar object, Oumuamua, and a later one named Borisov. Each new visitor brings new data, new mysteries, and new opportunities. As telescopes grow more powerful and sky surveys more detailed, astronomers expect to find many more such travellers. Each will have a different story to tell. Some may be icy comets, others may be rocky fragments. A few might even be something entirely unexpected. The more of them we find, the clearer our picture will become of the diversity of star systems across the galaxy. With every discovery, we step closer to answering the great questions. How common are Earth-like planets? How often do planetary systems form in ways very different from ours? And above all, how often do the seeds of life take root? The question of where life came from has fascinated human beings for thousands of years. Some people believe that life arose naturally on Earth from simple chemicals in the oceans. Others have wondered whether the first spark of life might have come from far away, carried across the vast emptiness of space. One of the most intriguing scientific ideas that explores this possibility is called Panspermia. Panspermia is a Greek word that roughly translates to seeds everywhere. In simple terms, the idea suggests that the building blocks of life, or perhaps even microscopic forms of life themselves, could travel from one world to another, hitching rides on cosmic travellers such as comets, asteroids, meteors, or even interstellar objects from distant stars. This does not mean that a fully developed alien creature is flying through space and landing on planets. Instead, it suggests something humbler but equally powerful: molecules, small but important, that could one day grow into living things if the right conditions are present. For centuries, panspermia was mostly a philosophical or imaginative idea, but in the modern age, with the rise of astronomy, chemistry, and space exploration, it has become a serious subject of scientific debate. Researchers are beginning to realize that the universe might not be as empty as it seems, and that the very dust and ice floating between the stars could be full of the ingredients for life. One of the most exciting developments in this field comes from the discovery of interstellar objects, bodies that did not form in our own solar system, but instead drifted into it from the galaxy beyond. The most famous examples so far include Oumuamua, discovered in the year 2017, and Borisov, discovered in the year 2019. More recently, astronomers have identified Threeey Atlas, another traveller from the stars. Each of these objects has provided a new chance to explore whether panspermia might really work in practice. When astronomers study interstellar objects like Threeey Atlas, they are not just looking at curious rocks. These visitors are like messengers from other star systems, carrying information about places that are light years away. As they journey through interstellar space, they are bombarded by radiation, cosmic rays, and collisions with tiny dust particles. Despite these harsh conditions, many scientists believe they might still hold on to precious materials, such as organic molecules or even prebiotic compounds. Organic molecules are the chemical ingredients made up of carbon, hydrogen, oxygen, and nitrogen, the same basic elements that make up all life on Earth. Prebiotic compounds are even more exciting. They are chemicals that may not be alive themselves but could help spark the development of life under the right conditions. Examples include amino acids, which are the building blocks of proteins, and nucleobases, which are needed for DNA and RNA. If objects like Threeey Atlas can carry these kinds of molecules across the galaxy, then panspermia becomes more than just a theory. It becomes a possible way that life could spread from star system to star system. Instead of life being rare and fragile, it could be something that the universe naturally distributes, planting seeds of potential across the cosmos. To understand why scientists take this idea seriously, we do not need to look only at distant interstellar objects. Our own solar system is full of clues. Take comets, for example. Comets are icy bodies that usually live in the outer regions of the solar system, such as the Kuiper Belt and the Oort cloud. The Kuiper Belt lies just beyond the orbit of Neptune and is home to countless small icy worlds. The Oort cloud is even farther away, a vast sphere of icy objects surrounding the solar system like a distant shell. When comets are disturbed, perhaps by the pull of a passing star or by the gravitational tug of a planet, they can fall inward toward the sun. As they do, their ices heat up and release gases, forming the bright tails that make comets so spectacular to see in the night sky. But comets are not just beautiful, they're also scientifically priceless. Studies of comets have revealed that they contain complex organic molecules on their surfaces and in their icy interiors. These molecules include simple sugars, alcohols, hydrocarbons, and even amino acids. In fact, the NASA Stardust mission, which launched in the year 2004, flew past Comet Wild 2 and collected samples of dust. When scientists studied those grains in laboratories on Earth, they found clear evidence of amino acids, the very same types of molecules that living organisms on Earth use to build proteins. This was a stunning discovery. It proved that the building blocks of life are not unique to Earth, but can also form in the cold, dark places of space. It also suggests that comets, asteroids, or other icy bodies may have bombarded the early Earth billions of years ago, delivering the raw materials needed for life to begin. If comets in our solar system can carry such molecules, then it seems very likely that interstellar objects like Threeey Atlas, which formed around another star, could do the same. In fact, they might even be better carriers, because their material could be older, more primitive, and less affected by the radiation of a nearby star. They could represent a kind of fossil chemistry from the earliest days of star and planet formation. If scientists can confirm that interstellar objects carry prebiotic materials, it would have enormous implications. It would mean that the processes that create life's building blocks are not rare or limited to a single solar system. Instead, they could be happening all over the galaxy, perhaps in nearly every star system. In other words, the universe may be full of the raw materials for life, drifting through space, waiting for the right conditions to combine into something more. Planets and moons that are rich in liquid water, heat, and stable environments might then take those materials and nurture them into full living systems. This would completely change how we see our place in the cosmos. Instead of Earth being a lonely and special cradle of life, it might be just one of countless nurseries where the seeds of life take root. When astronomers observed Threeey Atlas during its brief passage through our solar system, they noticed something fascinating. The object appeared to be wrapped in a thin dust cloud, likely made of small grains released during its journey. This dust might contain organic materials, tiny chemical breadcrumbs that could tell us about the environment where Threeey Atlas was born. If interstellar dust particles like these are common, then they might play a huge role in the birth of new star systems. As clouds of gas and dust collapse to form stars and planets, they could already be mixed with the ingredients of life, seeding new worlds before they even fully form. The discovery of water ice on Threeey Atlas makes the picture even more compelling. Water is one of the most essential ingredients for life as we know it. If interstellar objects regularly carry water ice and organic compounds, they might be the delivery vehicles that provide young planets with the things they need to eventually host life. This is similar to what scientists already believe happened in our own solar system. Billions of years ago, when Earth was still forming, it was struck again and again by comets and asteroids. These impacts may have delivered much of the water that now fills our oceans, as well as the molecules that helped kickstart biology. Interstellar visitors like Threeey Atlas may be doing the same thing for other planets, orbiting distant stars. One of the most interesting questions about interstellar objects is whether they remain intact during their journeys. Space is full of dangers, radiation, impacts, and the stress of passing close to stars. Some comets in our own solar system, for example, have been seen to break apart as they approach the Sun. If Threeey Atlas were to break apart, the fragments could scatter even more material across space, spreading dust and ice that might eventually land on planets or moons. In this way, the destruction of an interstellar object might actually help spread life's ingredients farther, acting like a cosmic dandelion puff sending its seeds into the wind. The study of objects like Threeey Atlas is about more than just rocks and dust. It touches on one of the greatest questions humanity has ever asked. Are we alone? If Panspermia is real, then life may not be an Earth-only phenomenon. It could be a galactic process, with seeds of life constantly being sown across countless worlds. Some of those seeds may never find a place to grow. Others may land on planets with oceans, atmospheres, and energy sources where they could slowly develop into living ecosystems. On Earth, life took billions of years to evolve from simple molecules into complex organisms. If the same processes are happening elsewhere, then the galaxy might be full of planets teeming with microbes, plants, and perhaps even intelligent beings looking up at their own night skies, wondering the same questions we do. As Threeey Atlas sped into our solar system from the distant reaches of interstellar space, astronomers and scientists around the world found themselves captivated by a question that, at first glance, might seem almost like a scene from a science fiction novel. Could this extraordinary cosmic traveller withstand the immense gravitational forces of the Sun without breaking apart? Unlike comets and asteroids that orbit comfortably within our solar system, objects that come from other star systems are completely untested in the extreme conditions they face when entering a new cosmic neighbourhood. Their structures, compositions, and internal strengths are unknown. Threeey Atlas, moving at staggering speeds of tens of kilometers per second, presented an exceptional case study for scientists eager to understand how tidal forces, those stretching and squeezing effects caused by gravity, might influence such an object. Tidal forces are not some abstract mystical concept. They are very real consequences of how gravity varies across an object. Imagine an object passing near a massive body like the Sun. The side of the object closest to the Sun experiences a stronger gravitational pull than the side farthest away. This difference in gravitational force, technically called a gravitational gradient, stretches the object, pulling it in slightly different directions across its length. If the object is weak, irregular, or made of loosely bound materials, this stretching can lead to cracks, fragmentation, or in extreme cases, complete disintegration. Scientists had witnessed similar phenomena in our solar system many times. Comets that venture too close to the Sun sometimes fall apart spectacularly, and even some asteroids are known to fracture under the stress of planetary encounters. In the case of Threeey Atlas, the concern was that the Sun's gravitational pull could have created an environment so extreme that a weaker object would have been torn apart during its rapid passage. Yet, as observations accumulated, it became clear that the visitor remained largely intact. Unlike some comets that develop long, bright tails of gas and dust when heated by the Sun, Threeey Atlas exhibited only very weak outgassing. Its activity, if it can be called that, was minimal, hinting that the object's structure was holding together despite the tidal forces acting upon it. This suggested that the body was sturdier than typical comets, likely composed of a more cohesive mix of rock and ice rather than fragile, volatile ices that evaporate easily under the Sun's heat. The journey of Threeey Atlas provided scientists with a rare, fleeting opportunity to observe the effects of tidal stresses on a truly interstellar object. Observing how it maintained its integrity, allowed astronomers to refine their understanding of how similar objects might behave in the future. The very fact that it survived its close approach without catastrophic breakup was both surprising and informative. It indicated that some interstellar bodies could travel vast distances across the galaxy and enter solar systems without disintegrating immediately, a vital clue for future observations and potential missions. While Threeey Atlas was fascinating in itself, its passage through our solar system also raised broader questions about humanity's preparedness for interstellar visitors. This was not a lone event. It was a glimpse of a larger cosmic reality in which objects from other star systems can, and likely will, cross our path more frequently than previously thought. Scientists and astronomers began to ask, if Threeey Atlas could come so close to the Sun and remain largely intact, how many more cosmic travellers might one day visit our solar neighbourhood? And crucially, are we ready to detect, study, and even explore them in detail? Fortunately, advances in astronomical surveys and technology are improving our ability to answer these questions. Instruments such as the Panoramic Survey Telescope and Rapid Response System, or PAN-STARRS, and the Asteroid Terrestrial Impact Last Alert System, known as the Atlas Survey, are constantly scanning the sky for fast-moving objects. These observatories are tuned to spot small, dim, or quickly moving cosmic bodies that might otherwise go unnoticed. Looking ahead, the next generation of telescopes promises to revolutionize our ability to detect interstellar visitors. The Vera C. Rubin Observatory, with its ambitious Large Synoptic Survey Telescope program, will dramatically expand our capacity to monitor the sky continuously and in high detail. This increased observational power means that astronomers will be able to identify interstellar objects earlier, track their paths more accurately, and potentially plan missions to intercept or study them up close. Early detection is vital because interstellar objects move extraordinarily fast compared to typical solar system bodies. Threeey Atlas, for instance, travelled at speeds so high that a conventional spacecraft would struggle to catch up. Planning missions to study such objects requires not only precise measurements of their trajectories, but also advanced propulsion technologies capable of reaching and matching their velocity. Concepts like ion propulsion systems, which use charged particles accelerated by electric fields, or solar sails, which harness the pressure of sunlight for acceleration, are promising tools for sending robotic probes to interstellar visitors. Such missions could allow scientists to gather unprecedented data about the composition, structure, and origins of objects from other star systems. The scientific value of these interstellar travellers cannot be overstated. Objects like Threeey Atlas carry chemical signatures that are frozen snapshots of conditions in distant star systems, offering unique insights into environments we cannot directly observe otherwise. By analysing their material, we can learn about the types of organic molecules present, the ways planetary systems form and evolve, and perhaps even the potential for life beyond Earth. For example, if future interstellar objects are found to contain complex carbon-based molecules, this could provide clues about the universality of the building blocks of life and the processes by which they travel between stars. In this sense, each cosmic visitor is not merely a rock or chunk of ice, but a messenger carrying invaluable information about the broader galaxy. Threeey Atlas was only the second confirmed interstellar object to pass through our solar system, the first being Oumuamua in 2014. Its unique trajectory and rapid passage through the inner solar system made it a case study for everything from orbital dynamics to the effects of tidal stress. By observing its behaviour, scientists could refine models predicting how interstellar objects move, how they react to gravitational forces, and how they interact with solar radiation. Even its lack of dramatic outgassing or tail formation provided clues. It suggested a sturdier, more resilient structure than that of typical comets, hinting at a diversity of object types waiting to be discovered beyond our solar system. The arrival of Threeey Atlas also forced astronomers to confront questions of planetary defense and preparedness. While interstellar objects are unlikely to collide with Earth due to the vastness of space, their high velocities make them difficult to study and intercept. Preparing for such objects is therefore both a matter of curiosity and scientific necessity. By simulating encounters with hypothetical future visitors, researchers can develop strategies for observation, tracking, and potential interception, ensuring that humanity can make the most of these fleeting opportunities. Perhaps the most exciting prospect lies in what we might learn from future interstellar visitors. Each object, depending on its origin, could tell a completely different story. Some may have originated in young, turbulent star systems where planetary formation is ongoing. Others could have travelled for billions of years through the cold interstellar medium, preserving ancient materials from the early days of their home stars. By studying them, scientists can effectively peer into the past and into regions of the galaxy that are otherwise inaccessible. Such studies could illuminate not just the chemistry and dynamics of distant star systems, but also the universal processes that shape planetary systems, including our own. Looking forward, the combination of improved detection, advanced observation, and innovative spacecraft technologies brings us closer to a future in which studying interstellar objects may no longer be a matter of chance. Missions could be planned in advance, equipped with instruments designed to analyze composition, structure, and potential organic content. By sending probes to these cosmic visitors, scientists might one day directly sample material from another star system, bringing back knowledge that would be impossible to acquire in any other way. This prospect opens a new chapter in space exploration, one in which the stars themselves are no longer unreachable points of light, but tangible destinations for study and discovery.